Somewhere at the very heart of galaxies, hidden beneath the gravitational dominance of supermassive black holes and cloaked in cosmic obscurity, lie strange and powerful structures, dense, ancient, and teeming with stars. These are the nuclear star clusters, the mysterious hearts of galaxies, far more compact and luminous than the star clusters we know from our galactic neighborhood. They are among the densest stellar systems in the known universe, yet their origins, evolution, and role in galactic life remain some of the most tantalizing puzzles in modern astrophysics. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine standing in the center of a galaxy, not just any point within its vast spiral arms, but the absolute center, where the gravitational landscape is most treacherous and the fabric of space-time bends most fiercely. Now picture a city of stars, packed so tightly that a single cubic light-year might contain millions of them, swirling in orbits dictated not just by gravity but by an ancient story of galactic violence and celestial birth. This is the domain of nuclear star clusters, a cosmic paradox of order and chaos, beauty and destruction, light and shadow. What makes nuclear star clusters so compelling isn't just their location or their density. It's the fact that they represent something ancient, almost primordial, like fossilized fingerprints left behind by the galactic processes that shape the universe we observe today. Found in the centers of galaxies, these clusters often coexist, and sometimes compete, with supermassive black holes. Yet, while the black holes consume and erase, nuclear star clusters preserve and remember. They are, in many ways, the living diaries of galaxies, holding records of mergers, migrations, and the chemical evolution of stars that existed when the universe was still young. Unlike the better-known globular clusters, which orbit galaxies like tiny, ancient moons, nuclear star clusters are embedded right in the galactic nucleus. And unlike the central bulge of a galaxy, which is diffuse and spread out, nuclear star clusters are incredibly compact. They can have masses reaching tens of millions of suns, squeezed into regions only a few light-years across. To put that in perspective, imagine compressing a significant portion of the Milky Way's mass into a volume smaller than the distance between our Sun and its closest stellar neighbor. The result would be a gravitational cauldron, hot, bright, and relentless. Astronomers have detected nuclear star clusters in over 75% of low to intermediate mass galaxies. That high percentage alone suggests that these objects are not cosmic anomalies but rather critical components in the life cycle of galaxies. Yet, for all their apparent ubiquity, they remain cloaked in mystery. How exactly do they form? Do they arise from the slow, chaotic accumulation of stars migrating inward over billions of years? Or are they born in violent galactic mergers, forged in the crucibles of cosmic collisions? Could they even be the remnants of ancient dwarf galaxies devoured by their larger host? One prevailing theory suggests that nuclear star clusters form through the infall of globular clusters. Over time, through a process called dynamical friction, globular clusters spiral into the center of their host galaxy, eventually merging to form the dense, centralized stellar population of a nuclear star cluster. This migration is driven by gravitational interactions that rob the clusters of their orbital momentum, drawing them inward. As they coalesce, the result is a dense, multi-age population of stars, some young, some ancient, locked in the galactic core. Another school of thought proposes that nuclear star clusters form in situ, meaning they are born directly in the galactic center through repeated episodes of intense star formation. In this model, gas funneled into the galactic center cools, collapses, and forms stars in waves, building the cluster layer by layer. This process might be triggered by bar instabilities in the galaxy's disk, or by tidal interactions with other galaxies. Over time, these waves of central star formation create the compact and complex structures we see today. In truth, both mechanisms might be at play. Observations of nuclear star clusters show a mix of stellar populations, with evidence of both ancient and relatively recent star formation. This blend suggests a hybrid formation model, where star clusters fall inward while gas-rich inflows contribute to new stellar births in the center. The cluster thus becomes a layered time capsule, each generation of stars recording a chapter of its host galaxy's evolution. But there's more. some nuclear star clusters don't exist alone. They share their galactic nucleus with a supermassive black hole, creating a delicate cosmic dance between light and darkness. The Milky Way, for instance, hosts both a nuclear star cluster and a supermassive black hole, Sagittarius A, at its center. This coexistence raises fascinating questions. Did one form before the other? Do nuclear star clusters feed the black hole with stars and gas, or does the black hole regulate star formation within the cluster? Is it possible that black holes actually grow inside nuclear star clusters? This idea, that supermassive black holes can form within the dense environment of a nuclear star cluster, is gaining traction. In such crowded environments, stellar collisions and massive star formation could lead to the creation of intermediate mass black holes, which might eventually merge and grow into the behemoths we see in massive galaxies. This could be a missing link in our understanding of black hole seed formation, one of the great unsolved problems in astrophysics. Furthermore, nuclear star clusters are astrophysical laboratories for extreme stellar dynamics. In such high-density regions, stars interact far more frequently than in typical galactic environments. These interactions can lead to rare phenomena, blue stragglers, stellar mergers, hypervelocity stars, and even tidal disruption events, where stars are shredded by the gravitational pull of a nearby black hole. In this sense, nuclear star clusters are not just remnants of galactic history, they are active, evolving systems where stellar life and death play out on accelerated timescales. Their importance doesn't stop there. By studying nuclear star clusters in distant galaxies, we gain insight into the early universe. Many of the stars in these clusters formed more than 10 billion years ago. Their chemical compositions tell us about the conditions of star formation at epochs when the universe was only a few billion years old. In a way, they are fossils from the cosmic dawn, offering rare, direct clues about galaxy formation in the ancient cosmos. Yet, observing these clusters is no easy task. Being located at the galactic center means they are often obscured by dust, gas, and bright background starlight. Advanced instruments like the Hubble Space Telescope, James Webb Space Telescope, and ground-based observatories with adaptive optics are vital for resolving these tiny, luminous cores in distant galaxies. With higher-resolution imaging and spectroscopy, we can begin to disentangle their stellar populations, measure their motion, and trace their evolutionary history. More tantalizing still is the discovery that not all galaxies have nuclear star clusters. Some galaxies, especially massive ellipticals, seem to lack them entirely, housing only a central black hole. Why is that? Is it simply that the cluster was swallowed by the black hole long ago? Or do certain galactic environments inhibit nuclear star cluster formation altogether? Understanding these distinctions could help us draw a clearer map of galactic evolution across the Hubble sequence. In addition, some dwarf galaxies contain only a nuclear star cluster and no discernible black hole, making them ideal test beds for studying early cluster formation in isolation. Interestingly, there is mounting evidence that many of these dwarf galaxies may have once been part of larger systems and were stripped down by gravitational interactions, leaving behind only their dense central clusters. This leads to the theory that some nuclear star clusters we observe today might actually be the stripped cores of cannibalized galaxies, floating as ghosts in larger galactic systems. In fact, this theory could explain some of the mysterious ultra-compact dwarf galaxies, UCDs, found around large galaxies like Centaurus A or the Fornex cluster. These UCDs could be nothing more than orphan nuclear star clusters, cosmic remnants of a galactic devouring. Their status as possible leftovers of galactic cannibalism gives nuclear star clusters a haunting legacy. Each one might be a tombstone for a galaxy that once was, a forgotten host whose identity was erased through gravitational conflict, leaving behind only the indestructible jewel at its core. In this way, nuclear star clusters don't just tell us about how galaxies live, they speak to how galaxies die. Their survival through galactic mergers and stripping events makes them among the most resilient structures in the universe, outlasting the vast disks, spiral arms, and even the stellar halos of their parent galaxies. And still, their formation raises paradoxes. For instance, how can such dense structures even remain stable over billions of years? Why don't they collapse into black holes or disperse due to chaotic gravitational interactions? The answer may lie in their unique stellar dynamics. Nuclear star clusters seem to be thermally relaxed, meaning they have reached a state of gravitational equilibrium, where stars distribute their energy in such a way that the whole structure remains bound and stable despite constant internal interactions. But this doesn't mean these clusters are static, far from it. Stars continuously migrate, collide, and evolve. Compact remnants like neutron stars and white dwarfs accumulate in the core, and mass segregation causes heavier stars to drift inward while lighter ones are pushed outward. This internal reorganization may even influence the long-term fate of the nuclear cluster. It could lead to the formation of central density cusps, regions where the stellar density increases dramatically toward the center. And in such high-density zones, collisions between stars can become inevitable, leading to stellar mergers that create unusually massive stars or even runaway collapse scenarios that may birth intermediate mass black holes. In fact, some of the most massive nuclear star clusters are suspected to harbor these intermediate black holes at their center, a mysterious class of objects long theorized but only recently observed with any degree of certainty. These objects could represent the missing evolutionary link between stellar mass black holes and the supermassive giants anchoring massive galaxies. Nuclear clusters, with their tightly packed stellar environments, might be the best places to find them. Moreover, the coevolution of nuclear star clusters and central black holes is a major focus of modern astrophysics. While in massive galaxies the black hole dominates, in lower mass galaxies the nuclear star cluster tends to be more massive than any central black hole. This inverse scaling hints at an evolutionary transition. Do black holes gradually grow at the expense of the nuclear cluster? Or does the presence of a nuclear star cluster regulate black hole growth by funneling gas and stars inward in a controlled way? This question touches the heart of the long-standing debate about how supermassive black holes achieve their mass so quickly in the early universe. In the Milky Way, we are fortunate enough to observe our own nuclear star cluster up close. Despite being cloaked by thick clouds of interstellar dust, observations in the infrared spectrum reveal a stunning and chaotic region filled with young, massive stars, ancient stellar remnants, gas clouds, and the imposing gravitational influence of Sagittarius A, our central black hole. This cluster spans about 4 parsecs, 13 light-years, and contains more than 10 million solar masses worth of stars. It's an incredibly diverse and turbulent region, where stars move at speeds of hundreds of kilometers per second, and where star formation continues even today, unusual for such a dense, gravitationally hostile environment. This ongoing star formation in such a violent locale raises intriguing possibilities. What processes could trigger or support star formation in a region so dominated by tidal forces from the black hole? Observations suggest that massive gas clouds occasionally fall into the galactic center, get compressed by gravitational shear, and ignite short bursts of star formation before being shredded. Some of the most massive and short-lived stars in our galaxy have been detected in this region, stars that live fast and die young, sometimes exploding as supernovae within just a few million years. These violent events have profound consequences for the evolution of the nuclear star cluster. Supernova explosions inject energy and turbulence into the surrounding environment, reshaping the interstellar medium and influencing the next wave of star formation. Meanwhile, their remnants, neutron stars and black holes, accumulate in the cluster core, contributing to the dynamical friction and mass segregation mentioned earlier. In this way, nuclear star clusters are not only repositories of stellar history, they're engines of ongoing galactic evolution. Even more remarkably, nuclear star clusters might play a role in the gravitational wave landscape of the universe. Within these environments, where stars are densely packed, close encounters and in spirals become more common. This raises the possibility of frequent black hole mergers and neutron star collisions, producing gravitational wave signals detectable by instruments like LIGO, Virgo, and LISA in the future. The implications are enormous. By studying these signals, we might be able to probe the internal dynamics of nuclear clusters light years away, offering a form of remote sensing across cosmic distances. What's also intriguing is how nuclear star clusters differ based on their host galaxy's morphological type. In spiral galaxies, nuclear clusters are often complex, multi-generational systems with ongoing star formation. In contrast, those in elliptical and spheroidal galaxies tend to be older, redder, and more metal-rich, pointing to a more static history. This diversity hints at how environment and galactic history shape the structure and evolution of nuclear star clusters. It also adds complexity to our models. No single formation scenario may apply universally. Interestingly, nuclear star clusters can also act as barometers of galactic health. Their presence, structure, and star formation activity can indicate whether a galaxy has undergone recent mergers, interactions, or starburst events. In this sense, they serve not just as stellar clusters but as diagnostic tools, revealing the evolutionary path taken by their host galaxies. Another layer of mystery is their chemical complexity. Spectroscopic analysis shows that many nuclear star clusters contain multiple stellar populations with varying metallicities. This suggests repeated cycles of star formation, punctuated by inflows of enriched gas and possibly even the accretion of smaller star clusters. The result is a chemically layered system, a cosmochemical mosaic that tells the story of galactic recycling over eons. Yet, despite their compactness, nuclear star clusters are not immune to galactic forces. In galaxies undergoing major mergers, tidal forces can disrupt or distort the cluster. In some cases, nuclear star clusters might even be ejected or destroyed, contributing their stars to the inner halo of the merged galaxy. This may explain why some elliptical galaxies appear to lack central clusters entirely. They may have once had them, but those clusters did not survive the chaos of collision. Still, others survive the ordeal, and in doing so, they may offer a rare glimpse into ancient merger events. Some nuclear clusters exhibit kinematic signatures, like counter-rotating stellar components, that hint at complex formation histories involving mergers of multiple systems. By decoding these signals, astronomers can reconstruct ancient cosmic events, like detectives parsing a galactic crime scene. And if that wasn't enough, some of the brightest nuclear star clusters in the universe are found in active galactic nuclei, AGN, galaxies with accreting black holes that outshine entire galaxies. In these systems, the nuclear star cluster must survive amid powerful radiation, jets, and winds emitted by the central engine. That these clusters can exist in such hostile environments is a testament to their density and resilience. With future instruments like the Extremely Large Telescope, ELT, James Webb Space Telescope, JWST, and Nancy Grace Roman Space Telescope, our view of nuclear star clusters will only sharpen. These observatories will allow us to resolve individual stars within distant clusters, measure precise stellar motions, and study the detailed chemistry of their stars. They may even help us answer the ultimate questions: how common are intermediate mass black holes in these clusters? What role do nuclear star clusters play in the birth of supermassive black holes? Are they relics of the earliest galaxies? One thing is certain: nuclear star clusters are more than just cosmic curiosities. They are keys to understanding galactic evolution, black hole formation, and stellar dynamics in extreme environments. They are time machines, laboratories, and survivors all at once, clusters that defy destruction and illuminate creation. Their duality, being both monuments of ancient cosmic architecture and sites of ongoing astrophysical drama, makes nuclear star clusters a profoundly rich subject of study. Despite being tightly packed stellar metropolises, they are not relics frozen in time. Rather, they are continuously evolving systems, subjected to an intense ballet of gravitational interactions, inflows of interstellar gas, supernova explosions, and even the cannibalism of neighboring star clusters. They are, in every sense, alive, changing, adapting, growing, and occasionally, perhaps, dying. One fascinating line of inquiry being pursued by astrophysicists is how nuclear star clusters can trigger or suppress galactic activity on larger scales. Because they sit in the gravitational low point of galaxies, they can act like regulators, influencing the inflow of gas into the galaxy's central regions. This is crucial in understanding feedback mechanisms, the processes by which energy and momentum from stars, supernovae, and active black holes are injected back into the interstellar medium, affecting subsequent star formation across the entire galaxy. In this sense, a nuclear star cluster may act not only as a cosmic witness to galactic evolution, but as a participant in shaping it. Observational campaigns are now revealing nuclear star clusters in galaxies far beyond the local group. Using instruments like the Multi-Unit Spectroscopic Explorer, MUSE, on the Very Large Telescope, VLT, astronomers can dissect the light from these clusters in remarkable detail. This allows for the mapping of stellar velocities, revealing rotation curves, signs of past mergers, and possibly hidden companions like intermediate mass black holes. With JWST now fully operational, even fainter and more distant nuclear star clusters are coming into view, some at redshifts that place them only a few billion years after the Big Bang. These discoveries offer the tantalizing possibility of witnessing nuclear star cluster formation in real time across cosmic epochs. Indeed, the evolutionary role of nuclear star clusters in the early universe cannot be overstated. Some theories posit that before galaxies developed the prominent bulges and large disks we see today, their centers were first populated by compact, massive star clusters. These clusters may have acted as gravitational seeds, attracting gas and stars to build up larger galactic structures around them. In this model, nuclear star clusters predate the galaxies themselves, reversing our conventional understanding of galactic growth. They could be the primordial cores, the spark that initiated the ignition of the galactic engines we see across the night sky. Another dimension to nuclear star clusters comes from the realm of stellar exotica. The extreme density of these environments means that they are breeding grounds for rare stellar objects, millisecond pulsars, X-ray binaries, cataclysmic variables, and even Thorne, Sitco objects, hypothetical stars formed by the collision of a neutron star and a red supergiant. The odds of close encounters in these clusters are astronomically higher than in normal stellar fields. These interactions not only shape the evolution of individual stars but create a feedback loop that influences the overall dynamical structure of the cluster. In some clusters, astronomers have observed hypervelocity stars, stars moving so fast that they are being ejected from the galaxy entirely. One explanation for this phenomenon is that these stars interacted with a binary black hole system at the center of a nuclear cluster. Such interactions can sling stars away at tremendous speeds via gravitational slingshot effects, turning them into stellar escapees traveling through intergalactic space. These high-speed events offer indirect evidence of black hole binaries, a phenomenon predicted by theory but difficult to detect directly. This brings us to one of the most deeply intriguing questions. Are nuclear star clusters precursors to supermassive black holes, or are they the byproducts? In low-mass galaxies, we often observe only the cluster and no central black hole. In high-mass galaxies, the black hole dominates, and the nuclear star cluster is absent or disrupted. In intermediate cases like the Milky Way, both coexist. This gradient suggests an evolutionary path where black holes may form inside clusters and eventually consume them, or where clusters give rise to black holes through runaway stellar mergers. This opens up a broader line of inquiry into galactic scaling relations, such as the correlation between black hole mass and the stellar velocity dispersion of a galaxy, the M-sigma relation. Are nuclear star clusters part of this scaling, or do they follow a different rulebook? Several researchers have begun to explore this by plotting cluster mass versus galaxy mass, or cluster luminosity versus central velocity dispersion. Surprisingly, some data sets suggest that nuclear star clusters and central black holes follow nearly parallel scaling relations, hinting that they might be complementary products of the same physical processes. This idea has sparked the concept of central massive objects, CMOs, a category that encompasses both nuclear clusters and black holes. Perhaps galaxies form a CMO through whichever process is more efficient in their specific environment, be it gas accretion and collapse, favoring black holes, or dynamical friction and cluster migration, favoring nuclear clusters. In simulations of early galaxy formation, we see these central regions form incredibly quickly, sometimes within a few 100 million years after the Big Bang. These protonuclear clusters form in dense pockets of gas that cool rapidly and undergo bursts of star formation. The first stars, often massive and short-lived, rapidly evolve and explode as supernovae, enriching the surrounding gas with heavier elements. This chemical evolution sets the stage for subsequent generations of stars and may also create conditions ripe for black hole formation. These simulations support the idea that nuclear star clusters are foundational to the emergence of galaxy structure, serving as gravitational anchors that stabilize the surrounding disk and funnel material inward. Some nuclear star clusters have also been found to exhibit asymmetric shapes, suggesting ongoing interactions with their environment. For example, the cluster may be elongated, lopsided, or show signs of rotation misaligned with the galaxy's disk. These features may arise from past mergers or off-center star formation, possibly caused by uneven gas inflow. Others show double nuclei, which may result from two clusters in the process of merging, or from a disrupted cluster that split due to a powerful gravitational interaction. These irregularities serve as real-time evidence of the chaotic evolutionary paths that these clusters endure. In a more speculative vein, some researchers have proposed that dark matter might influence the evolution of nuclear star clusters. While clusters themselves are primarily composed of normal, baryonic matter, they sit at the very center of the galaxy's dark matter halo. This may affect the gravitational potential in which the cluster resides, influencing its shape, stability, and even the rate of star capture. If dark matter consists of exotic particles that can weakly interact with regular matter, it's possible, though not proven, that it could slightly alter stellar motions or even collect in the cluster's core, contributing to unseen mass. Though this is still highly theoretical, it adds yet another dimension to the puzzle. Then there's the question of time. In the grand arc of cosmic history, how long do nuclear star clusters last? Are they stable for billions of years, or are they transient structures destined to be dismantled by the very black holes they orbit? Some models suggest that a cluster can persist for most of a galaxy's life, gradually being eroded by tidal forces or consumed by a growing central black hole. Others posit that many clusters are episodic, forming in bursts during active merger periods and slowly fading into the background during quiescent epochs. The answer likely depends on galaxy type, size, environment, and merger history. As our computational models grow more sophisticated, aided by machine learning and big data processing, we are beginning to simulate entire populations of galaxies over cosmological timescales. These models now include detailed prescriptions for the formation and destruction of nuclear star clusters, allowing us to track their life cycles within a cosmological framework. With this new power, we can ask not just what a single cluster can tell us, but what patterns emerge across thousands, or millions, of galaxies. And yet, for all this complexity, for all this depth, a nuclear star cluster remains, at its heart, a simple idea: stars bound together by gravity, existing in one of the most extreme and consequential environments in the universe. They are cosmic paradoxes, dense yet delicate, ancient yet active, silent yet seething with energy. They are formed from violence and persist through harmony. They are not only beacons at the centers of galaxies, they are the centers themselves. In contemplating nuclear star clusters, it's impossible not to marvel at the exquisite balance of chaos and order that defines them. These aren't just collections of stars, they are finely tuned, self-regulating ecosystems. Despite residing in some of the most tumultuous environments in the cosmos, where gravity can shred matter, radiation can sterilize molecular clouds, and black holes can bend space-time, nuclear star clusters endure. They adapt. They evolve. And in doing so, they bear witness to the full spectrum of galactic life, from formation to maturity, and sometimes even to death. At their densest, the stellar densities within a nuclear star cluster can be millions of solar masses per cubic parsec. To put that into perspective, if you replace the space around our Sun with a nuclear star cluster, the sky would blaze with thousands of stars at night, some so close they'd cast shadows. This extreme proximity affects everything: stellar evolution, collisions, interactions, and even the very way stars age. Binary systems are more common, and gravitational interactions are frequent. Stars are often pushed into high eccentricity orbits, which can lead to tidal stripping or stellar cannibalism. In this pressure cooker environment, a phenomenon known as runaway stellar collisions may occur. This happens when a star grows too large from successive mergers and begins to collapse under its own gravity, potentially forming an intermediate mass black hole, IMBH. These elusive objects, ranging from a few hundred to a few thousand solar masses, are among the most sought-after mysteries in astrophysics today. If confirmed, they would represent a critical evolutionary bridge, proof that stellar mass black holes can grow into the supermassive behemoths that anchor galaxies. Some theoretical models suggest that IMBHs could be common in nuclear clusters, especially in those formed early in the universe's history. Because these clusters provide both the fuel, stars and gas, and the gravitational conditions required for black hole growth, they could be the ideal breeding grounds for such objects. And if these black holes exist, their interactions, such as spiraling into the center, merging with other black holes, or accreting matter, would generate gravitational waves, potentially detectable by next-generation observatories like LISA, Laser Interferometer Space Antenna. The prospect of gravitational wave astronomy transforming our understanding of nuclear star clusters is not far-fetched. Consider a dense cluster in a dwarf galaxy, harboring an IMBH. If that black hole merges with another black hole or captures a neutron star, the event could release ripples in spacetime that traverse the cosmos. By detecting these signals, astronomers could not only confirm the presence of an IMBH but also extract details about the cluster's mass distribution, stellar density, and even its merger history. In a way, gravitational waves might become our ears in places where light cannot reach. Beyond black holes and gravitational waves, the chemical makeup of nuclear star clusters tells its own detailed story. These clusters often contain multiple stellar populations, each with unique metallicity signatures. Metals, in astronomical terms, refer to all elements heavier than hydrogen and helium. The first generation of stars in a nuclear cluster likely formed from primordial gas, producing metal-poor stars. Later generations, forming from gas enriched by supernovae and stellar winds, show higher metallicities. By analyzing the spectral fingerprints of stars within a nuclear cluster, astronomers can effectively reconstruct its star formation history, tracing back billions of years. This chemical stratification is significant because it proves that nuclear star clusters experience recurrent gas inflow and starburst episodes. These episodes may be triggered by galactic interactions, bar instabilities, or secular processes that drive gas inward over time. Each influx of gas reignites star formation, rejuvenating the cluster and adding new layers to its already complex stellar architecture. Such repeated rejuvenation cycles raise further questions about the limits of cluster growth. Is there a mass ceiling beyond which a nuclear cluster destabilizes or collapses into a central black hole? Do these rejuvenation events eventually exhaust the local gas supply, leading the cluster to go dormant? Or do the violent processes at the center of a galaxy inherently regulate growth through feedback mechanisms, supernovae, winds, and jets that expel gas before too much star formation can occur? In massive galaxies, where central black holes outshine their nuclear star clusters, this feedback becomes even more critical. AGN feedback, the outpouring of energy from an active galactic nucleus, can inhibit further gas infall, effectively starving the nuclear cluster of the material needed to form new stars. In these scenarios, the cluster becomes a fossil, preserving the memory of ancient starbursts but incapable of future growth. This interplay between a nuclear star cluster and its central black hole becomes a tug-of-war over matter and energy, each influencing the other's fate. Intriguingly, observations of dwarf galaxies, particularly ultra-compact dwarfs, UCDs, have revealed systems that blur the line between a galaxy and a nuclear star cluster. Some UCDs may, in fact, be stripped remnants of galaxies, where tidal interactions have removed the outer stars, leaving only the dense nuclear cluster behind. These galaxy cores without galaxies are compelling evidence for the destructive power of gravitational encounters in densely populated environments like galaxy clusters. They also suggest that nuclear star clusters can survive even the most violent galactic fates, acting as long-lasting relics of cosmic history. In this way, nuclear star clusters become more than just structural features. They are archaeological records, dense cosmic archives holding clues to past mergers, starburst epochs, black hole births, and galactic cannibalism. Their masses, compositions, kinematics, and morphologies are all data points in the grand story of how galaxies grow, evolve, interact, and sometimes vanish. The presence of double or triple nuclei in some galaxies further adds to the complexity. For example, in the Andromeda Galaxy, M31, high-resolution imaging has revealed a double nucleus structure, with two bright peaks embedded in a larger, eccentric stellar disk. One interpretation is that these are the remnants of a past nuclear cluster merger, or perhaps a displaced cluster orbiting around a central black hole. These asymmetries may not last long on cosmic timescales, but during their existence, they offer rare windows into transitional phases of nuclear cluster evolution. Another interesting anomaly is the existence of nuclear disks, which are flattened structures of stars or gas found within the inner tens of parsecs of some galaxies. While distinct from traditional spherical clusters, nuclear disks often coexist with nuclear clusters or represent transitional forms. Their dynamics differ significantly, with rotation playing a larger role than random stellar motion. Understanding how nuclear clusters and disks interact could shed light on how angular momentum is transferred in galaxy cores and how material spirals into central black holes. Ultimately, the more we learn about nuclear star clusters, the more questions arise. How do they differ in low-surface brightness galaxies, which are faint and diffuse? What role do they play in galaxies undergoing quenching, where star formation suddenly ceases? Could their behavior differ in galaxies with non-standard dark matter halos, or in isolated field galaxies versus cluster galaxies where interactions are frequent? We stand on the cusp of a new era in extragalactic astronomy. With observatories like JWST pushing our view deeper into time, and missions like LISA preparing to detect gravitational wave signatures from merging black holes within dense stellar environments, the coming years may well unravel the remaining secrets of these enigmatic clusters. New surveys may detect nuclear star clusters in unexpected places, or find them behaving in ways that challenge our current models. As our instruments grow sharper and our theories more precise, the once shadowy role of nuclear star clusters in the cosmic narrative becomes increasingly central. No longer just points of light lost in galactic cores, they are emerging as pivotal players in the grand orchestra of cosmic evolution, the architects of stability, the cradles of black holes, the tombs of galaxies, and the spark that may have birthed galaxies to begin with. They are not just clusters of stars. They are the memory of galaxies. And as we peer deeper into their mysteries, nuclear star clusters begin to reveal a narrative not just of stars and matter, but of time itself, a timeline woven into the gravitational heart of galaxies. These clusters are not transient fireworks in the sky. They are persistent, evolving archives of the universe's own memory. Every star inside them is a timestamp, a relic from an era long past, a witness to epochs of turbulence, quiescence, mergers, and rebirth. Together, these stars encode stories of ancient collisions, of black hole births, of gas infall and starburst, of core collapse and cosmic equilibrium. This leads to one of the most provocative and cutting-edge theories in astrophysics: the idea that nuclear star clusters may act as time capsules for the early universe. Because of their high stellar densities and preserved chemical signatures, some researchers now propose that we can use these clusters to reconstruct the conditions of galaxy formation in the first billion years after the Big Bang. In particular, the oldest stars in these clusters, those with the lowest metallicities, are candidates for being population 2 or even population 3 remnants, the first stars ever formed in the cosmos. Though true population 3 stars, made of only hydrogen and helium, completely devoid of heavier elements, are yet to be directly observed, their theoretical signatures are imprinted in the next generations. If such stars ever collapsed into black holes, their remnants may still lurk in the dense cores of nuclear clusters today. By analyzing stellar abundances and dynamics, we might uncover the fingerprints of these primordial ancestors, traces of the first light that ever existed. But to unearth such secrets, we require tools that operate not only across distance and time but also across complexity. The environments in which nuclear star clusters exist are deeply nonlinear. They're governed by chaotic systems where gravity, radiation, fluid dynamics, and quantum effects intersect. Numerical simulations have therefore become indispensable. Using supercomputers, researchers now model the lives of nuclear clusters across billions of years, accounting for gas cooling, star formation, feedback, tidal stripping, and even relativistic effects near central black holes. These simulations have revealed fascinating behaviors, such as core oscillations, where the cluster's core periodically contracts and expands due to interactions between stars and stellar remnants. Some models even show gravithermal catastrophes, runaway contractions of the core caused by energy exchange processes that mimic thermodynamic behavior. These events can result in black hole formation, cluster disruption, or even the ejection of massive stars, flung across the galaxy like bullets of light. And still, despite their complexity, nuclear star clusters remain oddly elegant. They often follow surprisingly well-defined scaling laws, akin to how planets in our solar system obey Kepler's laws. Observations show tight correlations between nuclear cluster mass and galactic luminosity, velocity dispersion, and galaxy morphological type. These relationships suggest that nuclear clusters are not random features. They are inevitable outcomes of galactic evolution, sculpted by the same fundamental physics that shapes spiral arms and dark matter halos. In the Milky Way, our own nuclear star cluster is a quiet yet dynamic place, orbiting the supermassive black hole Sagittarius A with a population of stars that includes both old red giants and hot, young blue stars. The presence of these young stars, located within a few light years of the black hole, remains a paradox. How could stars form in such an intense tidal environment, where the gravitational pull of the black hole should prevent gas clouds from collapsing? Several theories have been proposed, including in situ formation from dense accretion disks and migration of stars formed elsewhere. This remains one of the great unresolved mysteries of our own galactic core. Moreover, our Milky Way's nuclear star cluster offers a unique laboratory for testing general relativity and the behavior of matter in strong gravitational fields. The precise orbits of stars around Sagittarius A, particularly the so-called S-stars, have been measured over decades. These observations have confirmed predictions of Einstein's theory, including gravitational redshift and periastron precession. Future instruments, such as the Extremely Large Telescope, ELT, will enhance our ability to measure even finer deviations, potentially opening doors to new physics beyond general relativity. And then there's the question of interaction, how nuclear star clusters interact with the broader galaxy. In galaxies with bar structures, such as the Milky Way, bars funnel gas toward the center, potentially feeding nuclear clusters and triggering starbursts. This creates a self-reinforcing loop. Gas flows inward, ignites new stars, increases mass, deepens the gravitational well, and attracts even more gas. The nuclear star cluster thus becomes both a product and driver of galactic dynamics. But this cycle can be disrupted. A galaxy merger, for instance, can tilt the balance dramatically. As galaxies collide, their nuclear star clusters may spiral toward each other, eventually coalescing into a single, more massive structure. During this process, stars can be flung out into tidal streams, black holes may merge or be ejected, and the central regions of the galaxy can be completely restructured. Such mergers are expected to be common in the early universe, where small proto-galaxies constantly collided and reassembled. Hence, many of today's nuclear clusters may be ancient survivors of galactic trauma, patched together from multiple generations of cosmic history. Some may even be hybrid entities, containing both stellar components from original clusters and captured stars from the host galaxy's bulge or disk. This hybridity makes their study all the more fascinating, as it reflects not just internal dynamics but also the larger-scale galactic and cosmological environment in which they live. In the frontier of discovery lies the idea of hidden, nuclear star clusters, clusters that may be completely obscured by dust, embedded within dense star-forming regions, or drowned out by the light of an active galactic nucleus. With instruments capable of penetrating dust, such as near-infrared or X-ray telescopes, astronomers are beginning to detect such concealed clusters. These discoveries challenge prior assumptions about cluster prevalence and suggest that nuclear star clusters may be even more common than previously thought, simply hidden in plain sight by the complexities of galactic cores. This evolving picture reshapes our understanding of the universe's architecture. Just as stars form in clusters, it seems that galaxies themselves may have clustered hearts, dense nuclei that shape their development from the inside out. Nuclear star clusters serve as the beating hearts of galaxies, pumping out stars, regulating inflow, dancing with black holes, and anchoring the entire structure with their gravity. They are not passive bystanders of cosmic evolution. They are the engineers of the galactic soul. And as these engineers of the galactic soul persist through cosmic time, their role continues to expand beyond the gravitational domain. They may even play a subtle role in chemical and biological evolution on a galactic scale. Consider the implications of nuclear star clusters as cosmic accelerators, dense regions where high-energy radiation, magnetic fields, and frequent supernovae can significantly affect their surrounding interstellar medium. Supernova explosions within nuclear star clusters seed nearby gas clouds with heavy elements like carbon, nitrogen, oxygen, and iron, the building blocks of planets and life. These elements, forged in stellar cores and violently released in stellar deaths, are expelled outward in galactic fountains, mixing with cooler gas that may eventually collapse to form new stars and planetary systems. The proximity of nuclear clusters to galactic centers, regions rich in molecular gas, means that their influence on chemical enrichment may be far-reaching. In this way, nuclear star clusters contribute not just to the gravitational shaping of galaxies, but to the cosmic distribution of life-essential ingredients. Now imagine such a process happening over billions of years, continuously recycling matter through birth and death. Nuclear clusters become not just record-keepers of the past, but catalysts of future complexity, subtly guiding the galaxy's potential to support life-bearing worlds. Some scientists have speculated that the inner regions of galaxies, once dismissed as too violent or chaotic to support life, might actually host planetary systems stabilized by the deep gravitational wells created by nuclear clusters. These planets could have shorter orbital periods, receive more starlight from nearby stellar neighbors, and endure vastly different environmental conditions than those in calmer galactic suburbs. But there's also a darker side to this narrative. The gravitational interactions, high radiation flux, and frequent stellar collisions in nuclear clusters create an environment that is as dangerous as it is creative. Gamma ray bursts, relativistic jets, black hole accretion, and stellar ejections all contribute to an atmosphere of cosmic violence. A planet within a few light-years of a dense nuclear cluster might be bombarded by radiation intense enough to sterilize its surface regularly. And yet, this tension between destruction and creation is what makes nuclear clusters such profound subjects of study. They embody the universe's duality, the ever-present interplay of birth and obliteration. As we look to the future, several upcoming and proposed missions promise to revolutionize our understanding of nuclear star clusters. The James Webb Space Telescope, JWST, has already begun to pierce the veil of dust and galactic centers, revealing hidden clusters with unprecedented clarity. Its powerful infrared capabilities allow astronomers to detect the cooler, older stars in these clusters, which are invisible to optical telescopes. JWST's observations will help reconstruct the formation histories of these clusters with exquisite detail, including the timing and duration of their starburst episodes. Meanwhile, the European Extremely Large Telescope, ELT, with its 39-meter mirror, is expected to deliver the sharpest images of nuclear star clusters ever obtained from Earth. It will resolve individual stars even in distant galaxies, enabling precise measurements of their motions, ages, metallicities, and interaction dynamics. This kind of data will shed light on whether certain nuclear clusters are more rotationally supported, whether they contain stellar mass black holes that have not yet merged, and how their dynamics evolve with age. Another key advancement will come from gravitational wave astronomy, as observatories like LISA and DESIGO begin listening to the universe in a completely new way. These instruments will be particularly sensitive to low-frequency gravitational waves, the kind produced by mergers involving intermediate mass black holes within dense clusters. Detecting these signals would confirm the long-suspected presence of such black holes in nuclear star clusters and offer direct insight into how galaxies grow their central supermassive black holes over time. The discovery of even a single nuclear star cluster based intermediate mass black hole merger would be a paradigm shift. It would prove that such environments are capable of not only forming these objects but also bringing them together, a critical piece in the cosmic puzzle of black hole growth and galaxy formation. Yet for all the incredible tools at our disposal, some mysteries remain maddeningly elusive. For instance, there is still no universal consensus on how nuclear clusters form in the first place. Do they arise purely from in situ star formation, as gas is funneled into the galactic center over time and ignites into stars? Or are they assembled by the infall of globular clusters, dragged in by dynamical friction and merged at the core? Some models suggest a combination of both, where early starbursts lay the foundation, and migrating clusters add mass and complexity later on. This hybrid formation theory is particularly compelling because it explains the multiple stellar populations often observed within nuclear clusters. Some stars show signs of being ancient and metal-poor, likely formed early and in place. Others exhibit younger, more metal-rich signatures, consistent with globular cluster origins or more recent gas-driven star formation. The fact that such diverse populations coexist within a few light-years of each other is a testament to the dynamical complexity of these clusters and the multi-phase processes that build them. In fact, nuclear star clusters and globular clusters are more closely related than they might appear. Some researchers now see them as part of a continuum, differentiated not by type but by mass, environment, and evolutionary history. In dwarf galaxies, the distinction between a large globular cluster and a small nuclear cluster can blur entirely, especially if the nucleus becomes the dominant component after tidal stripping. This continuum hypothesis is bolstered by the discovery of nuclear clusters that resemble globular clusters in size and luminosity, but occupy the central regions of dwarf galaxies. Could these be relics of ancient galaxies stripped bare by interactions? Or are they the progenitors of modern globular clusters, forged in the hearts of galaxies long gone? Whatever their origin, these objects are part of a grander tapestry. Every cluster is a node in a web of cosmic processes that stretches from the Big Bang to the present, linking stellar evolution, galactic dynamics, black hole physics, and even the emergence of life. The more we study them, the more we see how deeply interconnected the cosmos truly is, and how small scales and large scales are mirrors of one another, with nuclear star clusters reflecting the behavior of galaxies, and galaxies echoing the forces that govern stars. They are the crossroads where all cosmic roads converge. And though they are small by galactic standards, just a few parsecs across, they may contain the blueprint of cosmic evolution itself, folded into a dense knot of stars, black holes, gas, and memory. But perhaps what is most captivating about nuclear star clusters is that they seem to exist at the threshold of cosmic order and chaos, where deterministic laws meet stochastic processes, and where the elegance of gravity collides with the wild card of stellar dynamics. These clusters challenge our definitions, blur the lines between different classes of astronomical objects, and force us to question what we thought we knew about the architecture of the universe. In this boundary region, stars don't just orbit, they interact. Unlike stars in more diffuse galactic neighborhoods, the stars and nuclear clusters are in close proximity, often separated by only a fraction of a light-year. As a result, stellar collisions are not just possible, they're inevitable. When two stars pass close enough, gravitational interactions can lead to dramatic outcomes. One star might be ejected from the cluster at hypervelocity speeds, while the other gains energy and moves inward. Or worse, they may collide, forming a merged object that temporarily becomes a blue straggler, hotter and more massive than expected for its age. These interactions affect the cluster's energy distribution and evolution, creating feedback loops that reshape its core structure. It's also within these chaotic environments that stellar exotica are born: millisecond pulsars, X-ray binaries, and perhaps even neutron star mergers, which are responsible for the creation of heavy elements like gold and platinum. Given the high stellar density, nuclear star clusters are among the most likely places in the universe for such rare and energetic events to occur. In fact, some of the most powerful gamma-ray bursts and gravitational wave signals may originate from these clusters, signals that travel across billions of light-years to briefly whisper their secrets into our instruments. This makes nuclear star clusters natural laboratories for testing extreme physics, not just of gravity, but of nuclear reactions, relativistic effects, and particle interactions. In the vicinity of a supermassive black hole, the space-time curvature becomes so intense that even light is distorted. Stars on eccentric orbits around these black holes become perfect test particles to explore post-Newtonian effects, such as frame dragging and geodetic precession, phenomena predicted by Einstein's general relativity but observable only under the most extreme conditions. Take, for example, the star S2, which orbits Sagittarius A with a period of about 16 years. Its close approach takes it within just 120 Australian dollars of the black hole, about 3 times the distance between the Sun and Pluto. As it swings around, its motion reveals subtle effects that differ from Newtonian predictions, allowing astronomers to directly test general relativity in a strong field regime. And where one such star exists, there are likely hundreds more, waiting to be observed, each providing another data point in the grand experiment of cosmic physics. The precision required to study such stars has driven the development of advanced instrumentation, including adaptive optics, interferometry, and integral field spectroscopy. Instruments like gravity, part of the VLTI, Very Large Telescope Interferometer, have already achieved unprecedented resolution, enabling us to trace star motions with microarcsecond accuracy. This level of detail allows for not just orbit determination, but for probing the mass distribution of the cluster, revealing whether dark matter or stellar remnants lurk in its depths. And the discoveries just keep coming. Some nuclear star clusters have been found to rotate, a property once thought unlikely given their small size and assumed isotropy. This rotation, when coupled with flattening and elongation, hints at anisotropic velocity distributions, possible merger histories, or even ongoing angular momentum transfer from infalling gas. Such complexity underscores that nuclear star clusters are not simple star balls. They're structured, evolving systems whose current forms are the result of billions of years of gravitational negotiations. In fact, the rotational properties of nuclear clusters are so informative that they are now used to infer the assembly history of their host galaxies. For instance, a nuclear cluster with significant rotation might suggest formation through gas inflow and disk star formation, while one that is pressure-supported may have been built more through globular cluster accretion. These are the kinds of signatures that help astronomers read the cosmic story written into galactic centers. There's also growing interest in the relationship between nuclear star clusters and nuclear disks. In some galaxies, particularly late-type spirals, nuclear clusters are embedded within larger, rotating disks of gas and stars, suggesting that star formation is not limited to a central point but may proceed in more extended structures. These disks may feed the clusters, act as angular momentum reservoirs, or even host embedded young star clusters that eventually migrate inward. The result is a layered nuclear architecture, with each layer telling a different chapter of a galaxy's evolution. Yet, for all the progress, nuclear star clusters remain one of the most enigmatic components of galactic structure. Even defining what qualifies as a nuclear cluster can be challenging. Should it be based solely on location? On density? On mass? On observational features like surface brightness? Each criterion has exceptions and edge cases, leading to a taxonomy that is still fluid and under debate. This ambiguity is both a frustration and an invitation, an open-ended puzzle that beckons further inquiry. And that inquiry stretches beyond just astronomers. Astrobiologists, too, have taken interest in these clusters, not just for their role in heavy element production, but for the stability of planetary systems within them. The dense stellar environment of nuclear clusters raises fascinating questions. Can stable orbits exist in such gravitationally complex neighborhoods? What happens to habitable zones when a nearby star goes supernova? Are rogue planets more common in these environments, ejected during stellar encounters and wandering in the core's gravitational well? Preliminary models suggest that while planetary systems may be rare or short-lived near the very center, they may still exist in peripheral regions of the cluster, especially in more quiescent galaxies with less violent black hole activity. Some scientists even propose that microbial life or extremophiles could theoretically survive on comets or asteroids in such environments, protected by layers of rock and ice. If so, nuclear clusters could become interstellar vaults of biological material, distributing life's ingredients through galactic winds and stellar ejecta. At this intersection of astrophysics and astrobiology, nuclear star clusters become more than just stellar assemblages. They become cosmic ecosystems, governed by the same fundamental laws that shape the structure of atoms, the spiral arms of galaxies, and the chemical bonds in DNA. The unity of these processes, across scale and complexity, is a testament to the profound interconnectedness of the universe. And as we continue our exploration, both through powerful telescopes and the algorithms of simulation, the secrets of these clusters will continue to unfold. Every new observation, every theoretical refinement, every high-energy signal from the heart of a galaxy, brings us one step closer to understanding not just how nuclear star clusters form, evolve, and interact, but how they reflect the very nature of the cosmos itself. They are the burning cores of stellar civilization, the secret keepers of black holes, the star forges of the early universe. And in their orbits and echoes, we hear the rhythms of time, the gravity of memory, and the breath of galaxies. As we continue to peel back the layers of mystery surrounding nuclear star clusters, it becomes increasingly clear that these seemingly compact structures are among the most multidimensional and revealing environments in the universe. Each one is a frozen snapshot of galactic history, a gravitational fingerprint pressed deep into the heart of its host, telling stories of ancient mergers, violent inflows, stellar migrations, and black hole births, all playing out over cosmic timescales in just a few parsecs of space. One of the most surprising revelations in recent years is that nuclear star clusters appear to be nearly ubiquitous in certain types of galaxies, particularly late-type spirals and dwarf ellipticals. Observations show that over 70% of such galaxies possess nuclear clusters, making them more common than even central black holes in some regimes. This challenges long-standing assumptions about the conditions necessary for cluster formation and suggests that nature finds a way to build these stellar hearts regardless of scale or galactic grandeur. Even more fascinating is the idea that nuclear star clusters and supermassive black holes are not mutually exclusive. Some galaxies, like our own Milky Way, host both, coexisting in a delicate gravitational ballet. In such systems, the nuclear cluster often extends beyond the black hole's sphere of influence, embedding the dark colossus in a sea of stars and stellar remnants. This coexistence raises important questions. Do nuclear clusters form before or after the black hole? Do they feed it? Compete with it? Stabilize it? One hypothesis gaining ground is the coevolution model, which suggests that nuclear clusters and black holes grow together, influenced by the same inflowing gas and subject to similar feedback processes. In this view, the nuclear cluster may serve as a reservoir or regulator, controlling the pace of black hole accretion and perhaps even shielding its host galaxy from runaway AGN activity. Alternatively, some models suggest a more competitive relationship, where early black hole growth may inhibit the formation of dense star clusters, or where the tidal forces from a black hole can disrupt and suppress in situ star formation. It's a complex, nonlinear dance, one that likely varies from galaxy to galaxy depending on mass, morphology, merger history, and environment. In lower mass galaxies, nuclear star clusters may dominate, while in massive ellipticals, black holes take center stage. But in that intermediate regime where both exist, we may find the key to unlocking how galaxies grow their cores, whether through violent episodes of starburst and AGN ignition or through slow, secular processes of accretion and star migration. Simulations are becoming increasingly sophisticated at modeling these possibilities. N-body codes, hydrodynamical solvers, and feedback algorithms are being combined to create multi-scale, multi-physics environments, where star formation, radiation pressure, gas dynamics, and relativistic effects all interact within the same virtual galaxies. These simulations have started to produce nuclear clusters that match observations not just in mass and size, but in density profiles, stellar populations, and rotational characteristics. Yet despite these advances, many observational limitations remain, especially when it comes to studying nuclear clusters in distant galaxies. Even with the Hubble Space Telescope and JWST, resolving clusters beyond a few tens of megaparsecs becomes increasingly difficult. To get around this, astronomers often use surface brightness profiles, spectral energy distributions, and kinematic tracers to infer the presence and properties of unresolved nuclear clusters. These indirect methods have revealed some of the most compact, massive nuclear clusters yet discovered, some with stellar densities reaching 10 solar masses per cubic parsec. Such densities are almost incomprehensible. In human terms, imagine a sphere just a few light-years across containing millions of suns, so tightly packed that the average distance between stars is less than a tenth of a light-year. In these conditions, not only are stellar collisions inevitable, but the overall evolution of the cluster is governed by relaxation timescales, energy equipartition, and core collapse processes that occur much faster than in typical star clusters. Indeed, some nuclear clusters may have already undergone core collapse, becoming mass segregated, with heavier stars and remnants, like white dwarfs, neutron stars, and black holes, sinking to the center. This mass segregation could lead to gravitational wave factories, where compact object binaries form frequently and merge within observable timescales. If so, nuclear clusters could be one of the primary sources of gravitational wave events detected by observatories like LIGO, Virgo, and the upcoming Einstein telescope. But beyond astrophysics, there is a more poetic dimension to all of this. Nuclear star clusters remind us that even the most violent and chaotic environments in the universe can give rise to beauty, complexity, and order. These are places where the earliest stars and the youngest stars share space, where light is born beside darkness, where entropy battles structure and sometimes loses. They are archives of cosmic memory, libraries without shelves, written in the languages of motion, mass, and metallicity. By studying them, we read not just about galaxies, but about the universe's fundamental desire to organize itself, against odds, against chaos, and against time. They are not just the ends of gravitational pathways. They are the beginnings of stellar civilizations, the seeds of something larger, something enduring. In the future, as AI-powered observatories and interferometric telescope arrays expand our reach and resolution, we may begin to detect temporal changes in nuclear clusters, shifts in brightness, star ejections, flare activity from dormant black holes. The day may come when we watch a nuclear cluster evolve in real time, tracking the life and death of its stars, witnessing the quiet absorption of a passing globular cluster, or even observing the flicker of a failed supernova swallowed by the central black hole. And maybe, just maybe, we'll find something unexpected. A signal, a pattern, an anomaly. Something that hints at a new kind of physics, or at an organizing principle not yet understood. Because if the universe hides its deepest truths anywhere, it's likely to be in its densest, most complex structures, where time folds, light bends, and gravity sculpts its most intricate masterpieces. Nuclear star clusters are not just astronomical objects. They are symbols of cosmic synthesis, where every force, every element, every epoch, and every idea collide and combine. They are the ultimate crucibles of creation and destruction, where galaxies breathe and remember. And in their glow, we catch a glimpse of eternity. They stand as glowing monuments at the very heart of galaxies, but nuclear star clusters are far more than just luminous concentrations of matter. They are dynamic records of time, forged by countless generations of stars and shaped by the gravitational forces that govern the universe. Every star within them is a witness to cataclysmic events, ancient mergers, and epochal transitions in their host galaxy's life. And perhaps more than any other known structure, nuclear star clusters embody the grand cosmic narrative, a story of collapse and formation, isolation and interaction, entropy and complexity. One of the reasons they are so rich in astrophysical insight is due to the diversity of their stellar populations. Unlike globular clusters, which are often formed in a single burst of star formation and thus contain stars of nearly the same age and metallicity. Nuclear star clusters are composites. Observations consistently show multiple stellar populations, spanning a wide range of ages, from stars that are several billion years old to those born just a few million years ago. This range implies that nuclear clusters have experienced repeated episodes of star formation, often in bursts, separated by periods of quiescence or disruption. This episodic formation history opens a window into the mechanisms that funnel gas into galactic centers, which is a non-trivial task. Galactic disks are typically rotating systems, and for gas to migrate inward toward the nucleus, it must lose angular momentum. Several processes can enable this. Bar-driven inflow, tidal interactions, galaxy mergers, and dynamical friction all play a role in stripping angular momentum from gas and stars, allowing them to spiral inward and contribute to the growth of the nuclear cluster. Each new influx of gas provides the raw material for another generation of stars, and the chemical fingerprints of those stars tell the story of their origins. Younger populations tend to be metal-rich, formed from material that has been enriched by earlier generations of supernovae. In contrast, older stars exhibit lower metallicities, a sign that they were born from primordial gas clouds or from less processed interstellar material. By analyzing the metallicity gradients within nuclear star clusters, astronomers can reconstruct their chemical enrichment histories, which in turn reflect the broader evolution of their host galaxies. Interestingly, this kind of analysis reveals another surprising trait. Nuclear star clusters often contain chemically decoupled cores. These are regions within the cluster where the stars differ markedly in their chemical composition from the surrounding populations. Such features suggest that localized, intense starbursts may have occurred, possibly triggered by discrete events like the accretion of a gas-rich dwarf galaxy or the inflow of a particularly massive molecular cloud. In a way, these chemically unique cores act like fossils of past starburst events, preserved in the present for us to decode. But the complexity doesn't stop at chemistry or age. Nuclear clusters are also kinematically diverse. Some rotate rapidly, others show signs of anisotropic velocity dispersions, and still others contain kinematic substructures, like counter-rotating disks or shells, that betray a tumultuous past of stellar migration and external accretion. These motions, measured through detailed spectroscopic studies, provide insights into the orbital dynamics and merger histories that shaped the cluster over billions of years. And in that motion, we sometimes find things we didn't expect. There have been observations of stars within nuclear clusters traveling at relativistic speeds, particularly those near central supermassive black holes. These S-stars, such as those observed near Sagittarius A, travel on highly elliptical orbits, reaching velocities of several thousand kilometers per second at pericenter. These stars are not only useful for probing general relativity, they are clues to the mass distribution, gravitational potential, and dynamical interactions occurring in the deepest parts of nuclear clusters. In some models, such stars are thought to be the survivors of binary disruption events, where a stellar binary wanders too close to the central black hole. One star is captured into a tight orbit around the black hole, while the other is ejected at incredible speed, perhaps becoming a hypervelocity star that escapes the galaxy entirely. Such mechanisms might explain how stars from the galactic center can be flung to the edges of the halo or beyond, essentially exporting the fingerprints of nuclear dynamics across galactic scales. This, in turn, opens a door to a whole new field of study: the relationship between nuclear star clusters and galactic halos. Could some fraction of the stars populating the outer regions of galaxies, especially in their stellar halos, have originated in nuclear regions? Could the presence of ancient stars in distant, isolated orbits be the result of interactions deep within a galaxy's core? It's a provocative idea, and one that underscores just how interconnected galactic structures truly are. And as we scale up from individual galaxies to clusters and large-scale structure, we begin to ask even bigger questions. What role do nuclear star clusters play in galaxy evolution on cosmological timescales? Are they the seeds of structure in the early universe, or the remnants of a different galactic era? Do all nuclear clusters follow similar evolutionary paths, Or are their stories as diverse as the galaxies that host them? Recent deep surveys of high redshift galaxies suggest that compact star-forming nuclei were more common in the early universe, particularly during the epoch of peak star formation around 10 billion years ago. These progenitors of today's nuclear clusters likely formed rapidly and violently, fed by rich inflows of cold gas from the cosmic web and shaped by the chaotic merger landscape of early galaxy assembly. As such, modern nuclear clusters may be the fossilized hearts of these ancient stellar forges, preserving the energy, structure, and memory of a time when the universe was young and turbulent. With instruments like JWST, we now have the capability to directly observe these early stages of nuclear cluster formation, capturing light that has traveled for billions of years. Already, hints of protonuclear clusters are emerging in young galaxies, dense, central starbursts embedded in dusty regions, compact and luminous, and displaying signs of intense feedback from both supernovae and AGN. These glimpses offer not just confirmation of theoretical models but inspiration for a new generation of cosmological questions. And as we dream of future missions, such as the proposed LUVOIR or HABEX space telescopes, or ground-based behemoths like the Extremely Large Telescope, ELT, we anticipate even greater insights. These tools will allow us to resolve nuclear star clusters at unprecedented distances, detect individual stars and clusters well beyond the local group, and perhaps even observe interactions between stars and black holes in real time. What might we discover? Perhaps quasi-periodic flares from stellar disruptions, or microlensing events from compact remnants, or maybe something entirely unexpected, a new class of transient, or a gravitational signature unlike anything we've ever seen. Because at the heart of every galaxy lies a mystery. A whisper of something ancient. A promise of discovery. And in the flickering light of nuclear star clusters, we find that the universe has not yet told us everything. But for all we do know about nuclear star clusters, there remains a profound sense that we're still only scratching the surface. Despite decades of observation, simulation, and theoretical refinement, these compact star-filled cores continue to defy simplification. Their diversity, their complexity, and their dynamic histories make them some of the most intriguing cosmic laboratories in all of astrophysics. One of the most persistent and fascinating questions concerns their origin stories. How do nuclear star clusters begin? Are they born in situ at the center of galaxies, with successive waves of gas falling inward and igniting bursts of star formation? Or do they form from the migration and merger of globular clusters, which spiral into the center over time due to dynamical friction? Or is it a blend of both? The dissipationless formation scenario, in which multiple globular clusters migrate inward and merge at the center, is supported by the structural similarities between some globular clusters and nuclear clusters. In this picture, the slow inward spiral of globulars is governed by gravitational interactions with the surrounding stars and dark matter. Over time, they deposit their mass and energy into the core, gradually building up a dense, complex stellar system. This mechanism is especially plausible in dwarf galaxies, where gas inflow might be limited and stellar mass dominates. However, observations of young stellar populations in many nuclear clusters complicate this picture. These young stars often appear centrally concentrated and coeval, strongly suggesting in situ star formation from centrally accreted gas. Such activity would require significant amounts of gas to reach the galactic nucleus, overcoming the angular momentum barrier through instabilities, bar-driven inflows, or tidal torques. The most likely explanation is that both processes contribute, with the dominant mechanism depending on the mass, morphology, and evolutionary history of the host galaxy. In lower mass galaxies, where globular clusters are relatively massive compared to the galaxy itself, dynamical friction can be highly efficient, making the globular infall pathway more important. In contrast, in larger disk galaxies, where gas inflow is more dynamic and sustained, in situ star formation can dominate nuclear cluster growth. This dual pathway model is supported by simulations that show hybrid formation processes can naturally reproduce the complex age and metallicity gradients observed in real nuclear star clusters. The outer layers of the cluster often show signs of older, more metal-poor populations, perhaps remnants of ancient globulars, while the core reveals younger, more metal-rich stars, born from centrally funneled gas. This inside-out structure acts like a geological cross-section, revealing the timeline of galactic processes that built the cluster over billions of years. In this way, nuclear star clusters are not just objects, they are processes, continually shaped by their environment and the cosmic events that play out around them. Each one is a stellar palimpsest, overwritten but never erased, carrying within it the signatures of interactions, feedback, infall, disruption, and rebirth. Another frontier of research lies in the connections between nuclear star clusters and active galactic nuclei, AGN. Some galaxies host both, a dense nuclear cluster and a central black hole that is periodically or persistently active. The interplay between these two components is an area of rich investigation. Can the nuclear cluster regulate the feeding of the black hole? Do outflows from the AGN quench or enhance star formation within the cluster? Are there feedback loops that operate over mere timescales, cycling between starburst and quasar phases? Theoretical models suggest that feedback from a growing black hole can disrupt gas inflow, preventing the formation of new stars and temporarily halting the growth of the nuclear cluster. Conversely, the gravitational potential of a dense nuclear cluster might act as a stabilizing anchor, allowing gas to accumulate and compress, triggering new rounds of star formation, even in the presence of AGN-driven winds or jets. This feedback regulation dynamic could be essential in explaining the tight correlations observed between nuclear cluster mass and host galaxy properties, such as the bulge mass and velocity dispersion. In some galaxies, nuclear star clusters and black holes may even co-evolve symbiotically, with star formation events delivering fresh gas and mass to the black hole, while the black hole's feedback governs the pace and extent of cluster growth. In this sense, the nuclear cluster is both a cradle and a regulator, participating directly in the most extreme processes that shape galaxies. There's even a tantalizing hypothesis that nuclear star clusters may give birth to intermediate-mass black holes, a long-sought, elusive class of objects with masses between stellar black holes and supermassive black holes. In the densest regions of nuclear clusters, dynamical interactions and mass segregation could lead to repeated collisions and mergers of stellar mass black holes, gradually assembling an intermediate mass object. If such a black hole reaches sufficient mass, it might then sink to the center, accrete further, and ultimately grow into a supermassive black hole, placing nuclear clusters at the very origin point of black hole genesis in the early universe. This could also explain why some ultra-compact dwarf galaxies, which may be the stripped remnants of larger galaxies, host both a dense star cluster and a central black hole. If nuclear clusters are survivors of galactic cannibalism, they might carry with them the cores and seeds of past civilizations, echoing events that played out hundreds of millions or even billions of years ago. This survival hypothesis is not just poetic, it's testable. By studying the properties of compact star clusters in tidal streams and isolated systems, we can begin to trace the evolutionary paths of stripped nuclei, identifying which ones might have once been the glowing hearts of larger galaxies. This, in turn, could allow us to reconstruct the galactic merger history of entire clusters and groups, using nuclear clusters as breadcrumbs left behind by long-vanished hosts. And what of the future? As the universe continues to expand, cool, and darken, galaxies will undergo profound transformations. Star formation will slow. Gas reserves will dwindle. But nuclear star clusters, with their dense stellar populations, long-lived stars, and gravitational depth, may remain among the last luminous structures, glowing faintly in the darkness of cosmic twilight. They may outlive their host disks, their spiral arms, their satellite systems. In a far future where galaxies themselves dissolve into darkness, it may be the nuclear clusters that endure, drifting like ancient lanterns in a universe grown cold. In their silence, they will carry the memory of starlight. Yet even as we contemplate the far future of nuclear star clusters, those ancient hearts that might one day become the final flickers of stellar civilization, we are also drawn to their unresolved mysteries that define the present. And one of the most elusive, yet tantalizing, questions is this: how many nuclear star clusters harbor central black holes that remain completely hidden from us? This is not a trivial question. In galaxies like our own, where Sagittarius A sits at the core of the Milky Way, we can observe the effects of a supermassive black hole directly. But in many other galaxies, especially low-mass or early-type galaxies, we often detect only the nuclear star cluster. There is no obvious X-ray activity, no flaring accretion disk, no relativistic jets. Yet that absence does not rule out the presence of a black hole lurking silently, its gravitational grip buried beneath layers of stellar light and dynamic motion. In these galaxies, the black hole may be quiescent, consuming only the smallest dribble of matter, giving off no visible signs of life. Or, it may be lost in the noise of the surrounding nuclear cluster, its gravitational influence too small to distinguish without ultra-high-resolution kinematic mapping. And herein lies the core of one of modern astronomy's greatest challenges: detection limits. The smaller the galaxy, and the smaller its potential black hole, the harder it is to find. This difficulty has led to significant observational biases in our black hole census. Most of our known supermassive black holes lie in massive elliptical galaxies, where they are easiest to detect. But nuclear star clusters dominate in lower-mass galaxies, and it is precisely these environments where the population of intermediate-mass black holes may be hiding. If we can probe these dense star clusters with sufficient precision, through high-dispersion spectroscopy, adaptive optics, or gravitational wave signals, we may be able to uncover an entire class of black holes that have so far remained invisible. And this leads to a compelling idea: nuclear star clusters as black hole nurseries. Over cosmic time, dense stellar environments can lead to runaway collisions among massive stars, producing black holes which then merge and migrate toward the center. In this scenario, the nuclear star cluster not only coexists with a central black hole, it actively creates it. The center of the cluster becomes a breeding ground for gravitationally bound compact objects, eventually leading to the formation of a black hole massive enough to seed further growth through accretion and merger. This idea is also deeply relevant for gravitational wave astronomy. As LIGO and future missions like LISA peer into the universe, they may detect gravitational waves from enspiraling black holes within nuclear clusters. These mergers might occur far more often than we currently expect, hidden deep within galactic nuclei, where stellar densities and interaction rates are extremely high. Such detections would allow us to map black hole formation channels with unprecedented clarity and confirm whether nuclear clusters truly are the cradles of intermediate mass and supermassive black holes. And let's not forget the role of dark matter in this picture. While nuclear star clusters are primarily baryonic, made of normal matter, we cannot ignore the potential influence of dark matter halos on their structure and formation. In particular, the interplay between baryonic collapse and dark matter concentration at the centers of galaxies may help determine how gas is funneled inward, how star formation is ignited or quenched, and how central masses grow. Some models suggest that cuspy dark matter profiles could promote the condensation of gas in the galactic core, triggering the formation of dense clusters. Others argue that dark matter heating from repeated starbursts could create core-like distributions, regulating further inflow. In either case, understanding the baryonic, dark matter interface in galactic nuclei is a crucial step toward explaining why some galaxies form massive nuclear clusters, others form supermassive black holes, and still others appear to contain both. This interplay may be governed by a complex balance between galaxy mass, angular momentum, merger history, and environmental factors, a symphony of variables that we are only beginning to understand. And within that complexity lies the promise of classification. As observations improve, astronomers are developing increasingly refined taxonomies of nuclear clusters, based on their morphology, kinematics, age spreads, and star formation histories. Some are disky, rotationally supported structures. Others are more spheroidal, dominated by velocity dispersion. Some contain embedded AGN or show signs of recent accretion. Others appear ancient, fossilized remnants of earlier times. Each type of nuclear cluster offers a different lens through which to view the processes that shape galaxies across time. Indeed, we may eventually come to see nuclear clusters not just as curiosities or end states, but as living chronicles of cosmic evolution. Like tree rings, each layer tells a story of accretion, collapse, ignition, and interaction. By reading those stories carefully, we gain not just knowledge of individual systems, but insight into the life cycles of galaxies themselves. And as our techniques continue to improve, using integral field spectroscopy, astrometric mapping, and machine learning applied to vast survey data, we may be able to trace the histories of tens of thousands of nuclear clusters in detail. We will see which galaxies had quiet, secular evolutions, and which were rocked by mergers. We will see where black holes formed early, and where they may still be forming. We will see the echoes of supernovae, the whispers of accretion, the relics of ancient collisions. We will, in short, begin to understand the cosmic hearts that beat quietly at the center of nearly every galaxy. And perhaps, in the deepest and most ancient of these clusters, we may one day find something entirely unexpected, evidence of exotic physics, relics from the Big Bang, or even, in the most speculative corridors of thought, the faint whispers of civilizations that once gazed up at their own stars and wondered if they were alone. Because when you stare into a nuclear star cluster, you're not just looking at stars. You're looking at time compressed, gravity sculpted, and matter transformed. You're looking at the cosmic memory of galaxies, written in orbits and light. And that memory is waiting for us to read it. As we press further into the enigma of nuclear star clusters, we confront yet another profound realization. These compact stellar environments are not just gravitational artifacts of galactic evolution. They are cosmic bridges linking the smallest galactic building blocks to the most massive, supermassive phenomena in the universe. In this context, nuclear star clusters serve as scales of transition, existing in a kind of mass and density middle ground. They are far more massive and dense than typical globular clusters, yet still orders of magnitude less extreme than supermassive black holes or active galactic nuclei. And yet, paradoxically, they sometimes cohabit with black holes at their centers. This duality has led to the concept of the central massive object, CMO, a term designed to describe the combined mass of a nuclear star cluster and or central black hole in any given galaxy. The fascinating trend is this: as galaxies become more massive, their CMOs shift from being dominated by nuclear clusters to being dominated by black holes. In low-mass galaxies, nuclear clusters tend to be more prominent, with central black holes either absent, small, or undetected. In high-mass galaxies, the reverse is true. Nuclear star clusters either disappear or become negligible compared to the black hole's overwhelming gravitational dominance. This trend hints at an evolutionary sequence, or a mass threshold that dictates which central component becomes dominant as galaxies grow and transform. What, then, dictates this transition? One hypothesis involves galactic mergers. During a merger between two galaxies, especially major mergers between galaxies of similar mass, the violent gravitational interactions can disrupt or destroy nuclear clusters, either by scattering their stars or by causing them to merge with the growing central black hole. This may be why massive elliptical galaxies, the byproducts of countless mergers, tend to lack nuclear star clusters altogether, but possess immense black holes. Alternatively, it's possible that AGN feedback plays a critical role. A rapidly accreting black hole can drive out gas from the galactic nucleus, heating and expelling the material that might otherwise have formed new stars in the nuclear cluster. In this feedback-driven model, black hole activity doesn't just coexist with the nuclear cluster, it actively halts its growth, stalling star formation and evaporating the reservoir of cold gas necessary to sustain the cluster's evolution. This may explain the curious observation that nuclear star clusters are incredibly efficient at converting gas into stars, perhaps more so than any other environment in the universe. Their compactness allows gas to be compressed to extreme densities, creating conditions ripe for rapid, high-efficiency star formation. However, this same compactness also means that they are vulnerable to black hole feedback, to tidal disruptions, to dynamical heating from mergers. The balancing act between growth and destruction plays out over billions of years and leaves its marks in the age distribution, kinematic structure, and chemical makeup of the cluster. Indeed, the chemical abundances within nuclear clusters are among the most informative relics we can study. Many clusters show clear evidence of multiple stellar populations, each with different metallicities, suggesting episodic star formation. These episodes often span gyre timescales, hinting that the nucleus of a galaxy remains an active, evolving environment long after the galaxy's main disk has quieted. The relative ratios of alpha elements, iron peak elements, and other heavy metals provide a chemical fingerprint of the interstellar medium at different points in the galaxy's history. In some cases, the nuclear cluster may even preserve the first stars formed in the galaxy, ancient population II stars that condensed in the very earliest bursts of star formation. These stars act like fossils, telling us about the conditions of the early universe in extreme detail. In dwarf galaxies, where chemical enrichment is slow, these relic stars can dominate the nuclear cluster's outer layers, while younger, metal-rich stars dominate the core, mirroring the inside-out formation pattern mentioned earlier. But even in their present-day form, nuclear star clusters are never static. Their internal dynamics continue to evolve. Mass segregation drives heavier stars and stellar remnants, like neutron stars and black holes, toward the center, potentially forming dense central cores of compact objects. These objects interact gravitationally, occasionally merging or forming exotic binaries, such as X-ray binaries or even gravitational wave sources. Theoretical models suggest that over time, this central concentration of dark remnants may influence the overall structure of the cluster, possibly leading to core collapse or the formation of intermediate mass black holes through repeated mergers. Such an environment is also perfect for stellar collisions. In the crowded cores of nuclear clusters, the average distance between stars can be less than a tenth of a light-year, close enough that direct collisions become non-negligible. These events can produce blue stragglers, stellar mergers, or even unusual transient events. And with the advent of all-sky surveys like LSST, there is a growing possibility that we may soon witness real-time transients emerging from these regions, luminous flares, microquasars, or other exotic outbursts. Beyond observational astronomy, nuclear star clusters are rapidly becoming a focal point in theoretical cosmology as well. Their potential role in seeding the early universe's black hole population makes them key players in the direct collapse scenario of SMBH formation. According to this idea, dense gas clouds in early protogalaxies may have bypassed normal star formation entirely, collapsing directly into massive black holes or nuclear clusters. Over time, such clusters could provide the gravitational anchor for continued accretion, eventually evolving into the quasars we now observe at redshifts c greater than 6, a time when the universe was less than a billion years old. To test this hypothesis, researchers use simulations that track the formation of nuclear clusters in dark matter halos at high redshift. These simulations show that violent dynamical instabilities in primordial galaxies can drive gas rapidly to the center, producing a burst of star formation followed by black hole formation in short order. If these processes occurred widely, then nuclear star clusters were not only common in the early universe, but may have been foundational to the emergence of the cosmic web as we know it. They are, in a sense, the missing link between the small-scale structures we can resolve in nearby galaxies and the large-scale, early universe structures visible in the cosmic microwave background and large-scale structure surveys. They carry the imprint of both local galactic evolution and global cosmological history. Even now, as we develop new instruments like the James Webb Space Telescope, researchers are using its infrared vision to peer into the dust-shrouded centers of galaxies, both near and far, to search for these nuclear clusters in greater detail. JWST's sensitivity enables us to distinguish the ages and metallicities of different stellar populations, study the faint remnants of dwarf galaxies long gone, and perhaps even detect protonuclear clusters forming in the first billion years of cosmic time. In the near future, extremely large telescopes, ELTs, with mirror diameters over 30 meters, will provide the spatial resolution needed to study the internal kinematics of nuclear clusters in unprecedented detail. This will allow astronomers to directly measure the gravitational influence of central black holes as small as 10 to the power of 4 solar masses and study the rotational dynamics, velocity dispersion, and structural profiles of clusters across all galactic environments. The questions nuclear star clusters raise are the same questions that have always defined astrophysics. Where do we come from? What forces shape the universe? What becomes of stars and galaxies when they grow old? In their dizzying densities, dizzying ages, and dizzying gravitational dances, nuclear star clusters hold answers, not just about galaxies or stars, but about the very architecture of space and time itself. And so we continue, drawn deeper into the luminous gravitational mysteries at the hearts of galaxies, those compact star-crushed cores we call nuclear star clusters. They are more than just the bright centers of galaxies. They are silent archivists, historians of the cosmos, with every star they contain acting like a page in a book spanning billions of years. But within this book, one of the most perplexing chapters remains unwritten. The question of why nuclear star clusters seem to form everywhere, across nearly all galaxy types, from spirals to spheroidals, even in isolated dwarf galaxies far from any cosmic commotion. This ubiquity implies a kind of fundamental universality, as though the laws of galactic evolution inevitably favor the creation of a central dense stellar cluster. Even in galaxies that show no evidence of past mergers or interactions, we still find these compact nuclei. This leads scientists to explore the possibility that nuclear clusters might represent a kind of default outcome in the evolution of baryonic matter under gravity, a minimum energy solution in which dissipative processes funnel gas and stars to the center over time. But this also poses a paradox. If nuclear star clusters are so widespread, why do some galaxies lack them entirely? Why are there examples, especially among early-type elliptical galaxies, where even a faint nuclear concentration is missing? One theory suggests that the most massive galaxies possess such strong tidal fields and black hole activity that they prevent nuclear clusters from forming or surviving. Alternatively, the black hole feedback mechanisms, where jets and radiation from an actively feeding black hole blow out central gas, may have sterilized the central region long ago. This selective presence of nuclear clusters hints at a dividing line in galaxy evolution, a boundary where the conditions flip from cluster formation to black hole domination. It's not necessarily a clean cut, it's a transitional spectrum. But understanding where this boundary lies, and what dictates which central structure will form, remains one of the open frontiers in astrophysics. An even more fascinating question emerges when we consider the evolutionary trajectory of nuclear star clusters over cosmic time. They may form early, but what happens to them afterward? Are they stable configurations, or are they destined to be destroyed? In some theoretical models, nuclear clusters act as intermediate evolutionary stages, eventually consumed by the black holes they help form. If enough mass collects at the center of the cluster through star migration, accretion, and collision, the core might collapse into a black hole, which then grows by devouring the cluster itself. Over billions of years, the nuclear cluster may slowly dissolve, leaving behind only a gravitational monolith in its place. In this sense, every nuclear star cluster could be seen as a potential seed of a future black hole, a ticking time bomb of gravitational collapse. And that's not all. There's mounting evidence that nuclear clusters might not just die through internal collapse. They may also be torn apart during galaxy mergers. When galaxies merge, their central regions are thrown into chaos. Tidal forces can disrupt or eject nuclear clusters entirely, especially if the encounter is particularly violent or involves galaxies of very different masses. This may explain the origin of some ultra-compact dwarf galaxies or naked nuclear clusters, stellar systems found far from any galaxy, containing stars tightly packed in a dense core, but lacking any galactic disk or halo. These may be the exiled hearts of once-living galaxies, cast adrift during ancient collisions. Such ejected clusters may retain complex internal dynamics. Without a host galaxy to shield them from external forces, they become gravitationally fragile, their outer stars slowly stripped by the intergalactic medium. Yet, they continue to burn, and they continue to orbit, sometimes as satellite objects around larger galaxies, relics of cosmic cannibalism. Observing these wayward nuclear clusters is like finding the fossilized remains of forgotten civilizations, evidence of galaxies that no longer exist. From another angle, nuclear star clusters may also be actively merging with globular clusters. Some galaxies, especially those rich in globular clusters, exhibit evidence that these satellite clusters have spiraled in over time, due to dynamical friction, and merged with the nucleus. This process would contribute both mass and complexity to the nuclear cluster, introducing older, metal-poor stars into an otherwise young or mixed population. This kind of stellar sedimentation could result in observable age gradients, and may also explain the unusually high masses of some nuclear clusters compared to their host galaxies. It's important to remember that nuclear clusters are not monolithic. They are not spherical star balls. Many show evidence of flattened, disk-like components, suggesting that rotational support plays a role in their structure. These stellar disks likely form during phases of gas inflow and starburst activity, and their presence can offer clues about the galaxy's merger and star formation history. In some cases, the nuclear cluster rotates in the opposite direction of the galaxy's disk, clear evidence that the material used to form it came from an external source, likely during a minor merger. The rotation curves of nuclear star clusters are being mapped in detail using cutting-edge spectroscopic instruments, revealing an astonishing variety of kinematic features: double nuclei, off-centered cores, spiral substructures, and more. These features tell us that nuclear clusters are dynamic, and that their evolution is still ongoing, especially in younger galaxies. With future missions such as the Nancy Grace Roman Space Telescope, LISA, and ground-based observatories like the 30-meter telescope and Giant Magellan Telescope, the study of nuclear star clusters is poised for a revolution. These instruments will allow us to detect and track gravitational waves from within galactic centers, observe faint stellar populations in distant clusters, and resolve internal motion of stars with exquisite precision. And perhaps, in time, this deepened understanding will help answer one of the most profound questions of all. Why do galaxies have hearts? Why do stars gather at their cores with such obsessive density? Why do some hearts turn into black holes while others burn on? Are nuclear star clusters a brief phase in galactic life, or are they foundational, everlasting structures? Are they passive observers of the universe's evolution, or are they active agents, steering the fates of galaxies from their gravitational thrones? They may even have something to tell us about the ultimate fate of galaxies in a dark energy-dominated cosmos. In trillions of years, long after the spiral arms have faded, the gas has cooled, and the stars have died, nuclear clusters may be the last lights of galactic memory, flickering quietly in a silent and expanding universe. They are the hearts of galaxies, and in their silence, they beat with the secrets of creation. If we could listen to the heartbeats of the cosmos, nuclear star clusters would pulse with the weight of billions of years, dense, luminous spheres of starlight compressing the very soul of a galaxy into a cosmic ember. They exist not only as structures of matter but as echoes of every force that shaped them: gravity, collapse, collision, birth, and death. They are where time seems most concentrated, where distance is most deceptive, and where the border between chaos and order is drawn thin. As the story of nuclear star clusters unfolds deeper into the observable and theoretical frontiers, the role of stellar remnants, black holes, neutron stars, and white dwarfs becomes impossible to ignore. These relics of stellar evolution are not evenly distributed throughout the cluster. Over time, mass segregation naturally pushes these heavy remnants toward the center of the cluster due to energy exchanges with lighter stars. This results in an increasingly dense core of dark objects, which may dominate the gravitational potential at the very center, even without the presence of a central supermassive black hole. Such dark cores can be difficult to detect, but their presence influences the velocities of stars around them. Stars near the center of the cluster exhibit higher velocity dispersions than can be explained by visible mass alone. This has led astronomers to propose that some nuclear star clusters may host intermediate mass black holes, IMBHs, black holes larger than stellar mass black holes but smaller than those found in galaxy centers. Finding definitive proof of such objects is a central goal of modern astrophysics, as IMBHs could be the missing link in black hole evolution, bridging the gap between supernova remnants and supermassive giants. These nuclear clusters may even act as gravitational wave factories, due to their ability to trap compact objects in tight orbits. Stellar mass black holes that find themselves in the dense core of a nuclear cluster may become gravitationally bound to each other or to a central IMBH, eventually in spiraling and merging. These mergers release bursts of gravitational waves, ripples in spacetime that missions like LIGO, Virgo, and the upcoming LISA, Laser Interferometer Space Antenna, aim to detect. What's remarkable is that these clusters might host multiple generations of black hole binaries, continually replenished by stellar evolution and mass segregation. Over cosmic timescales, this could result in a black hole-dominated cluster core, where the majority of the mass is invisible, yet the influence is undeniable. In such clusters, the luminosity is a facade, masking an interior governed by objects that emit no light. But beyond the physics, nuclear star clusters also force us to confront a more philosophical realization. They are not just scientific entities. They are cosmic relics, survivors of countless cosmic events, immune to galactic death, and resistant to time itself. They carry within them the earliest stars of their host galaxies, the chemical signatures of ancient supernovae, and the dynamical scars of past collisions. When we peer into a nuclear cluster, we are looking into a deep time machine, one that compresses the entire story of its galaxy into a few parsecs. The age gradients, metallicity spreads, and stellar population structures tell us what happened and when: gas inflows, starbursts, mergers, disruptions, collapses. These are not merely clusters of stars. They are memory cores of the universe. And yet, the more we learn about them, the more questions arise. For instance, why do some nuclear clusters form multiple components? Some are surrounded by extended stellar envelopes, others are embedded in nuclear disks. A few have been observed to harbor double nuclei, where two dense star clusters orbit each other tightly in a gravitational dance that seems frozen mid-merger. These phenomena imply an even more complicated formation history, perhaps involving successive cluster infall, or even dual episodes of central starburst activity. There's also the ongoing mystery of ultra-compact dwarf galaxies, UCDs, dense, star-rich spheroids that may in fact be the stripped nuclear clusters of larger galaxies. These UCDs are too small and bright to be considered typical galaxies, yet too large to be traditional globular clusters. Their dynamical masses and chemical abundances suggest they are the remnants of once larger systems, stripped by tidal forces during interactions with giant galaxies or clusters. If UCDs are indeed relic nuclei, then nuclear star clusters may be the most resilient structures in the universe, capable of outliving their host galaxies. This transforms them from mere galactic components into intergalactic wayfarers, witnesses to cosmic violence, and persistent messengers from times long past. Meanwhile, simulations have begun to explore the idea that nuclear clusters might form in the absence of galaxies altogether. In the early universe, before well-defined galactic structures had time to develop, gravitational instabilities in dense filaments of gas might have triggered direct collapse into dense stellar clusters. These primordial nuclear analogs could serve as the initial seeds for both cluster and galaxy formation, suggesting that galaxies may have grown around clusters, not the other way around. As this idea gains traction, it repositions nuclear star clusters at the foundation of cosmic structure formation, not merely the result of it. They may represent a primary condensation point, a gravitational sink around which matter coalesced in the young universe. If so, then these compact clusters are not just the oldest parts of galaxies. They may be the oldest structures in the universe still visible today. When we combine this with the possibility that some nuclear clusters host central IMBHs, we enter speculative but exciting territory. Could it be that the first stars formed in these clusters, and the first black holes grew within them? And could these have evolved into the seeds of quasars and eventually the titanic supermassive black holes we observe at the centers of galaxies today? This leads to an even bolder question. Is every supermassive black hole the tomb of a nuclear star cluster? Perhaps in their earliest forms, these clusters gathered stars and gas, formed compact centers, and birthed black holes that grew steadily until the light of the stars was drowned by gravitational darkness. Perhaps the light dies first, and the mass remains, a ghost cluster now known only by the influence of its black hole. And yet, in many galaxies, the stars survive. Nuclear clusters remain intact, glowing faintly beneath the galactic bulge, resisting obliteration by black hole or merger. They are not simply fossilized, they are still alive, still burning hydrogen, still birthing stars, still interacting dynamically in ways we are only beginning to understand. They are the laboratories of gravitational extremes. They are the engines of central starbursts. They are the cosmic archivists of galactic memory. And perhaps, just perhaps, they are the keystones of the universe's great architecture. Nuclear star clusters are not just astrophysical curiosities. They are gravitational dynamos, stellar melting pots, relics, labs, navigational beacons, and time capsules all at once. Their study combines the disciplines of galaxy formation, stellar evolution, black hole physics, cosmology, and even relativity. To understand them is to hold a magnifying glass to the center of everything. And the more we stare into them, the more they stare back. Their stare is ancient. Their gaze is not passive, it is revelatory. Nuclear star clusters are not merely watchers of cosmic history, they are participants in it, architects of their own evolution, and in many ways, the foundation stones upon which galaxies are built and rebuilt. In every corner of the observable universe where we find a galaxy of almost any shape or scale, we find evidence that these brilliant, compact centers have played a central role in guiding the flow of matter and the rhythm of star formation. To look inside a nuclear star cluster is to peel back a layered structure of cosmic archaeology. Each stratum, each population of stars, tells of a time when the galaxy was different. In some clusters, we see signs of multiple stellar generations, with newer stars rich in metals layered atop older, metal-poor populations. This layered complexity suggests an evolutionary cycle. Infalling gas triggers a burst of star formation, then supernovae and stellar winds blow the gas away, quenching activity, until a new episode of inflow begins the process anew. Some clusters may have undergone 5 or more such episodes over billions of years. This episodic pattern has been confirmed by spectroscopic surveys, which allow astronomers to deconstruct the light from a cluster and trace its chemical evolution. The presence of certain heavy elements like iron, magnesium, and calcium varies between populations and serves as a fingerprint of the kind of supernovae that seeded them. Type II supernovae from massive stars enrich a region quickly, while Type I supernovae take longer and contribute different elements. By measuring these, we can essentially date the layers of star formation, an interstellar dendrochronology, if you will. Another critical observation lies in the shapes of nuclear clusters. While some are spherical, many are flattened or even elongated, suggesting the presence of rotating stellar disks embedded within them. This points to a gas-rich origin at least for part of the mass, where angular momentum from inflowing material wasn't fully dissipated. These inner disks may rotate in the same direction as the host galaxy, or, curiously, in the opposite direction. When counter-rotation is observed, it often implies that the cluster has accreted gas from external sources, possibly through a minor merger or the infall of a gas-rich satellite galaxy. In the cases where counter-rotating disks are embedded inside nuclear clusters, the dynamics become fascinatingly complex. Stars on opposing orbits can interact, increasing the rate of gravitational perturbations, heating the cluster, and potentially altering its structure over time. These interactions also increase the probability of collisions and close encounters between stars, rare events in most galactic environments, but common in the dense cores of nuclear clusters. Some of these encounters may even produce blue stragglers, stars that appear younger and bluer than their neighbors, likely formed through stellar mergers or mass transfer. The presence of these blue stragglers in nuclear clusters could serve as a litmus test for how dynamic and turbulent their history has been. In the most extreme environments, where densities soar to over 10 million solar masses per cubic parsec, collisions could be so frequent that entire subpopulations of stars arise from merged systems. This creates a kind of stellar laboratory, where the rules of star formation, aging, and death operate under different, more extreme pressures than almost anywhere else in the universe. At the same time, nuclear star clusters often display a fascinating interplay between cooperation and conflict with their neighboring black holes. In galaxies that harbor both a nuclear cluster and a central black hole, Their mutual gravitational influences create delicate equilibria. The black hole may truncate the inner density of the cluster, preventing stars from forming too close to it. Conversely, the cluster may act as a shield, regulating the amount of gas that reaches the black hole and influencing its growth. It's a cosmic partnership of tension and balance. Recent simulations suggest that nuclear star clusters may even regulate their own survival through feedback. As stars form in the dense center, their winds and radiation heat and expel surrounding gas, temporarily halting further star formation. Over time, the expelled gas may cool and fall back in, triggering another burst. This feedback loop could explain why many clusters show bursty, discontinuous star formation histories, instead of a single monolithic age distribution. But beyond simulations and models, direct observations continue to surprise us. The Hubble Space Telescope and the James Webb Space Telescope have revealed nuclear clusters in galaxies billions of light-years away, appearing as mere points of light, yet holding tens of millions of stars. These observations suggest that the formation of such clusters began very early in the universe's history, possibly less than 1 billion years after the Big Bang. And here lies another mystery. How did such massive, complex structures form so quickly? This question challenges our understanding of galactic timescales. In the early universe, the conditions for star formation were extreme. Gas was more abundant but also more turbulent and metal-poor. Yet despite this, we see nuclear clusters that appear old, metal-rich, and dynamically relaxed, characteristics that imply rapid formation and early evolution. Some theories posit that these early clusters may have formed from runaway mergers of superstar clusters, or from the direct collapse of massive gas clouds, unimpeded by dust or fragmentation. It's even been proposed that nuclear clusters may have preceded the formation of galaxy bulges, growing independently, and eventually drawing stars and gas toward themselves, laying the foundation for the rest of the galaxy to form around them. If this is true, it would upend the traditional picture of galaxy formation, placing compact clusters at the core of cosmic architecture, rather than as products of it. Their resilience also inspires awe. In galaxies that have undergone major tidal interactions, nuclear clusters often survive even when the rest of the galactic structure is shredded. Tidal tails, star streams, and disrupted halos are all signs of violent gravitational interaction, but often, the nucleus remains intact, orbiting freely or becoming part of a new system. Some of these wandering nuclei have been observed as hypercompact stellar systems, so dense and luminous that their origins as former galactic hearts are unmistakable. And now, thanks to the next generation of telescopes and simulations, we're entering an era where these once faint objects will become high-definition laboratories of astrophysics. JWST, with its infrared capabilities, is already resolving nuclear clusters in dusty starburst galaxies. Upcoming gravitational wave observatories will allow us to hear the merging black holes hidden within them. The Vera C. Rubin Observatory, with its wide-field survey capability, will help track rogue nuclei and uncover populations of stripped clusters once lost to darkness. Each discovery brings new questions. What happens in the final stages of a nuclear cluster's life? Do they collapse into black holes, or fade as their stellar populations age out of the main sequence? Could the future of some galaxies be nothing more than a drifting, ancient nuclear core, a fossil memory glowing dimly against the blackness of the void? Or might nuclear star clusters outlive the stars themselves, dense enough to endure even after their luminous members fade into cold embers and stellar remnants? Could they be among the last coherent structures to exist, billions of years into the cosmic dark age, long after galaxies have stopped forming and stars have ceased to shine? If so, they may become the final candles in a dying universe. The heartbeats of the cosmos. Beating still. Beating alone. In that imagined distant future, where the universe has aged into senescence, and the last galaxies dim into obscurity, nuclear star clusters might be among the last bastions of visible matter, repositories of gravitational cohesion amid cosmic entropy. With their extreme densities and long-lived stellar populations, they may remain gravitationally bound even as galaxies are torn apart by the steady expansion of space. Like seeds preserved in stone, they could carry the chemical and dynamic memory of a cosmos that once teemed with creation. But before that distant end, they still have much to reveal. Modern astronomy is racing to decode these stellar enigmas. One of the more revolutionary frontiers is the effort to study nuclear star clusters not only as gravitational entities, but as chemical archives, deep reservoirs of information about the gas, stars, and dark matter that have passed through the galactic core over billions of years. By examining the spectroscopic fingerprints of stars in different regions of a nuclear cluster, astronomers can reconstruct detailed star formation timelines and uncover how these clusters enrich their environments. This level of precision is only possible because nuclear clusters host stars at all stages of evolution. Some stars are hot, massive, and young, products of the most recent starburst. Others are ancient red giants, dim and metal-poor, formed when the universe was young. Each population has its own story to tell, and together, they form a narrative more complete than any single type of star could provide. And then there's the question of angular momentum, a surprisingly complex issue in such tightly packed environments. While large galaxies often retain a coherent spin from their original formation, nuclear star clusters tend to have disordered or multidirectional angular momentum profiles, suggesting a chaotic assembly involving repeated mergers, gas inflow events, and gravitational torques. This complexity can only be understood through detailed integral field spectroscopy, a technique that allows astronomers to build full three-dimensional velocity maps of stellar motions within the cluster. These velocity maps often reveal that stars in the core move in more random directions, while those further out tend to rotate in a disk-like configuration. This kind of internal kinematic structure suggests that many clusters are dynamically evolved systems that have undergone a core collapse phase, where the central regions become denser and hotter due to gravitational energy transfer. In some cases, this collapse may have triggered the formation of a central intermediate mass black hole, a scenario that unites nuclear cluster evolution with black hole seed formation models. Meanwhile, theorists are refining our understanding of how repeated gravitational encounters within such clusters could produce exotic stellar phenomena. One example is the potential for runaway collisions, where massive stars or black holes sink to the center and merge repeatedly, creating a single supermassive object. This process might explain how some ultra-dense stellar systems could serve as black hole factories, building massive seeds long before galactic bulges or dark matter halos reached maturity. Moreover, nuclear clusters act as testing grounds for general relativity and gravitational dynamics under extreme conditions. In their crowded interiors, stars can experience close encounters that send them into eccentric orbits, sometimes passing mere astronomical units from the central black hole, if one exists. These extreme orbits could produce relativistic precession, gravitational redshift, and other effects that push the boundaries of Newtonian physics. In the coming years, instruments like the ELT, Extremely Large Telescope, and TMT, 30-meter telescope, may be able to resolve such orbits in nearby nuclear clusters, offering a new way to test our most advanced theories of gravity. Even more intriguing is the question of how these clusters interact with dark matter. Unlike stars and gas, dark matter does not radiate or interact electromagnetically, but it still influences stellar motions via gravity. Some theories suggest that nuclear star clusters may form within cusps of dark matter, left over from the earliest gravitational collapses. By studying the detailed stellar kinematics in the outer regions of clusters, we might detect signatures of dark matter influence, such as unexpected accelerations or deviations from predicted mass-to-light ratios. Conversely, other models propose that the dense baryonic mass of nuclear clusters may push dark matter away, heating it through gravitational interactions and carving out cores rather than cusps. If true, this would offer valuable constraints on the behavior of dark matter on small scales, something that has remained elusive despite decades of study. There's also an ongoing effort to use machine learning to decode the rich observational data associated with nuclear clusters. These systems produce enormous datasets, photometric, spectroscopic, kinematic, that resist simple categorization. AI models trained on simulations and high-resolution telescope data are now being used to classify nuclear clusters, estimate their ages, metallicities, and internal dynamics, and even predict the likelihood of them harboring a central black hole. One particularly exciting application of machine learning is in anomaly detection, identifying nuclear clusters that defy known patterns. These outliers could point to new evolutionary pathways, rare formation histories, or even exotic physics. Already, these tools have highlighted nuclear clusters with unexpectedly young populations, abnormal velocity dispersion profiles, and unusual chemical gradients, sparking new research questions about how such systems could have formed. Beyond science, there is an almost poetic beauty to these clusters. They are, in many ways, the closest thing we have to stellar cities, bustling, radiant, and ancient, with millions of stars packed together in neighborhoods more crowded than anything the Milky Way's outskirts could imagine. In their brilliance lies the fusion of chaos and order, of entropy and structure, of light and memory. To imagine being inside one is to enter a place where night never falls. The sky would be a dome of constant starlight, brighter than anything we know on Earth, every square arc-second bursting with the glow of neighboring suns. Shadows would not exist, because light would come from every direction. The very concept of isolation would vanish, every star gravitationally aware of its companions, every orbit intertwined in a cosmic web. Yet even in this crowding, each star follows its own path, its own lifetime, its own destiny. In the Milky Way, our own nuclear star cluster sits 26,000 light-years away, surrounding the central black hole Sagittarius A. It is perhaps the most extreme stellar environment in our galaxy, a place where stars whip around the black hole at thousands of kilometers per second, where some orbits have been tracked for decades to test Einstein's predictions, and where new stars continue to form from the funneling of interstellar gas. And it is only one among many. The Andromeda Galaxy has its own nucleus, a double nucleus, in fact, separated by a few light-years and orbiting a central black hole. The presence of this dual-core structure suggests a complicated dynamical history, possibly the merger of two former clusters or the outcome of long-term gravitational torques. Each galaxy has its story, and at the center of nearly every one is a nuclear cluster helping to tell it. Even in dwarf galaxies, we see these nuclei. The fact that such small systems can host such dense centers continues to challenge our understanding of how nuclear clusters form and evolve. Some theories suggest that these dwarf galaxies are more efficient at feeding gas into the nucleus, due to their weaker gravitational potential and lower rotational support. Others suggest that the nuclear cluster forms early and becomes the anchor around which the dwarf galaxy is built, a bottom-up view of galactic construction. And the mystery only deepens when we consider that not every galaxy has a visible nucleus. Some galaxies appear to lack nuclear clusters entirely, while others have replaced theirs with dominant black holes. What determines this fate? Is it random? Is it dictated by mass, merger history, environmental factors? Or does it come down to subtle differences in initial conditions, chaotic, butterfly effect ripples that echoed across billions of years? Perhaps the greatest mystery of all is not what nuclear clusters are, but what they choose to become. Some grow into quasars, igniting a central black hole that devours everything around it. Others fade, becoming dim fossil remnants in the darkness of aging galaxies. Some are torn apart in galactic collisions, their stars scattered across intergalactic space. And some persist, quietly burning, holding the center of their galaxy with unwavering gravity. They are cosmic crossroads, between light and dark, order and chaos, birth and collapse. To study them is to touch the pulse of the universe itself. And yet, for all the knowledge we have amassed, nuclear star clusters remain tantalizingly elusive, paradoxes wrapped in luminosity, each one a concentrated history of its host galaxy, compressed into a space only a few light-years across. What we know now is only a whisper of what they contain. Every new observation challenges the assumptions of the last. Every spectrum, every orbit, every light curve adds complexity to an already intricate portrait. Even the mass distribution within these clusters is difficult to pin down. The extreme densities mean that mass segregation, a process where heavier stars and remnants like neutron stars or stellar mass black holes sink to the center, can dramatically reshape the cluster's internal dynamics over time. These darker components, often invisible to telescopes, influence the visible stars through gravity alone, creating subtle imbalances and perturbations that can only be teased out through years of motion tracking and dynamical modeling. In the heart of the Milky Way's own nuclear star cluster, for example, astronomers have detected hints that a swarm of stellar-mass black holes may lurk just beyond the grasp of our instruments, perhaps numbering in the thousands. If true, this would make our galactic center not just a bright beacon of stars, but a hidden sanctuary of collapsed matter, an unseen menagerie of gravitational ghosts, circling quietly beneath the light. Such environments are perfect laboratories for gravitational wave astronomy. The high densities and dynamic chaos in nuclear clusters mean that compact binary systems, white dwarf pairs, neutron star duos, and black hole binaries, are more likely to form, harden, and eventually merge. The gravitational waves from these mergers are detectable across the universe, and future space-based observatories like LISA, Laser Interferometer Space Antenna, are poised to directly capture the tremors from within nuclear clusters, revealing details that even light cannot show us. This brings us to one of the boldest predictions in current astrophysics: nuclear star clusters as birthplaces of intermediate mass black holes, IMBHs. These elusive objects, with masses between 100 and 100,000 times that of the Sun, remain hypothetical in many cases. But if they exist, nuclear clusters are among the most promising locations to find them. Repeated stellar mergers in the core, gas accretion over time, and the natural gravitation toward mass concentration all make nuclear clusters ideal IMBH factories. Some observational candidates have emerged, stellar systems whose internal velocity dispersions, radiative emissions, or X-ray signatures hint at a central mass too large to be explained by stars alone, and yet too small for a supermassive black hole. These dark giants, if confirmed, could bridge a major gap in our understanding of black hole growth and provide the missing evolutionary link between stellar remnants and galactic leviathans. There is even speculation that the very first black holes, formed from primordial gas in the early universe, could have nested inside ancient nuclear clusters, quietly feeding, growing, and eventually launching themselves into the heart of larger galaxies as mergers proceeded. In this way, nuclear clusters may have acted as stepping stones in the cosmic web, ferrying black holes from their humble beginnings toward the massive engines that now shape galaxies. But while black holes often steal the spotlight, it's the stars themselves in nuclear clusters that continue to surprise. In some clusters, we find populations of extremely young stars, just a few million years old, formed in situ despite the hostile, high-radiation environment near galactic centers. These discoveries challenge our understanding of star formation thresholds, as such regions were long thought to be too hot and turbulent for new stars to condense. Instead, it appears that nuclear clusters can reignite their own growth by pulling in cool gas from spiral arms or galactic halos. This gas spirals inward, compresses under gravity, and triggers bursts of new star birth, sometimes forming tight disks of stars that rotate around the cluster's center, distinct from the surrounding spheroidal component. These stellar disks within clusters offer a snapshot of galaxy evolution in miniature, playing out the same dramas of accretion, feedback, and angular momentum exchange that shape galaxies on far grander scales. It is also in these clusters that we can watch the life and death of stars unfold in accelerated detail. Massive stars live fast and die young, some collapsing into neutron stars or black holes, others exploding as supernovae and enriching their surroundings with heavy elements. In a nuclear star cluster, the metal enrichment cycle is turbocharged by proximity. Supernova ejecta don't drift away into the void, but remain trapped, mixing back into the gas and seeding the next generation of stars with higher metallicity. Thus, each cluster contains multiple chemical fingerprints, from pristine hydrogen-helium stars forged in ancient epochs to metal-rich giants infused with the ashes of previous generations. No two nuclear clusters are the same. Each has walked a different path through the cosmos, each shaped by its own galaxy's mergers, accretions, winds, and collisions. And still, the mystery deepens. We now know that some galaxies host both a nuclear star cluster and a central supermassive black hole, living together in gravitational partnership. But others show only one or the other. Why? Could one evolve into the other? Are they competitors or collaborators? Do black holes destroy nuclear clusters as they grow, or do clusters seed black holes? The coevolution of these two structures may hold the key to understanding not just cluster dynamics, but the very nature of galaxy evolution itself. There are theories that nuclear star clusters could form before the black hole ever appears, acting as the gravitational magnet that draws in gas and primes the central region for black hole formation. Others suggest that clusters form around already established black holes, growing like coral reefs in the gravitational tides of their dark centers. And in some simulations, we see a delicate dance, the black hole slowly consuming part of the cluster even as the cluster shields it from further infall, creating a gravitational feedback loop that limits the growth of both. This mutual evolution likely depends on galaxy mass, morphology, and merger history, with lower mass galaxies favoring cluster formation and higher mass systems tilting toward black hole dominance. Over time, as galaxies merge and evolve, the balance can shift, with clusters being disrupted, consumed, or even ejected by gravitational recoil events after black hole mergers. Yes, entire nuclear clusters can be kicked out of galaxies if the black hole at their core merges with another and emits gravitational waves unevenly. The resulting recoil can launch the remnant black hole and its surrounding star cluster out of the galactic nucleus at velocities exceeding 1,000 kilometers per second. These recoiling nuclei become rogue wanderers, glowing in intergalactic space, dragging their ancient stellar memories behind them. Some of these have been detected: compact, high-velocity, off-center star clusters with unusual spectral signatures and no obvious host galaxy. They are orphans of cosmic violence, torn from their homes by the gravitational echoes of black hole mergers. In studying them, we glimpse not only the power of relativity, but the fragility of galactic order. And in all of this, there remains one final, haunting question. Are we living in a nuclear star cluster? The Sun resides far from the Milky Way's core, in a quiet spiral arm. But stars in the galactic center live in a different reality, a place of constant light, intense gravity, and perpetual motion. If life could arise there, it would experience a sky unlike any we know, and perhaps evolve under pressures and stimuli that would lead to utterly different forms of consciousness. Could civilizations emerge and thrive in such an environment? Or would the chaos of gravitational tides, radiation bursts, and nearby supernovae snuff them out before they begin? Some theories suggest that dense star clusters might actually be ideal for interstellar colonization, as distances between stars are so small that communication and travel would be vastly easier. If life ever did arise in such places, it may have burned bright and brief, like the stars around it, an epic but ephemeral flicker against the dark. Yet even in the silence that remains, the stars endure. And so, nuclear star clusters persist, silent, radiant testaments to the complex, often violent processes that shape the cosmos. They are both graveyards and nurseries, home to the ashes of ancient stars and the birthplaces of new ones. They hold the scars of galactic collisions, the echoes of long-dead quasars, and the molecular whispers of interstellar gas compressed into ignition. Their endurance across cosmic time makes them invaluable to the broader field of galactic archaeology. In essence, every nuclear star cluster is a layered archive, preserving a time capsule of chemical and dynamical records. When astronomers analyze the distribution of stellar ages and metallicities within these clusters, they are not just studying a group of stars, they are unraveling the full evolutionary arc of their host galaxy. And it's not only the stars within these clusters that are studied. The way these stars move is equally important. The motions of stars, especially in the innermost parsecs of the cluster, are deeply influenced by the presence of central massive objects. These kinematic signatures allow astronomers to detect invisible masses, possible intermediate mass or supermassive black holes, without directly seeing them. We can infer their presence through the way they warp the gravitational field, accelerate stars, and shape velocity dispersion profiles. One of the most extraordinary observational achievements in this domain comes from the study of the S-stars near the Milky Way's central black hole. These stars, some of which are members of the surrounding nuclear star cluster, move on eccentric, relativistic orbits that take them within light hours of Sagittarius A. Their motion not only verifies the presence of the black hole but also provides an empirical playground for general relativity, allowing scientists to measure gravitational redshift and Schwarzschild precession in real time. It's no exaggeration to say that nuclear star clusters are where astrophysics meets the limits of theory. They press against the boundaries of Newtonian mechanics, challenge our assumptions about stellar evolution, and invite us to think in terms of chaotic systems, quantum remnants, and relativistic feedback. Their interaction with galactic bars, for instance, reveals much about the secular evolution of disk galaxies. As stars and gas migrate inward along the gravitational torques of a bar structure, they pile up at the center, sometimes feeding the nuclear cluster, other times triggering a burst of star formation that alters the cluster's entire configuration. This process can repeat cyclically, and over billions of years, the cluster becomes a composite of many episodes of infall, ignition, and quenching. This makes nuclear clusters excellent indicators of a galaxy's internal dynamics and environmental history. For instance, in galaxies that reside in dense clusters or interact frequently with neighbors, the nuclear star clusters tend to be more massive, more metal-rich, and more dynamically complex. This suggests that environmental density plays a significant role in the long-term evolution and assembly of nuclear clusters. Conversely, in isolated or low-mass galaxies, the nuclear clusters are often more pristine, less chemically enriched, less massive, and more homogeneous. These are the untouched fossils of an earlier universe, giving us a glimpse into the formation of structures in more quiescent environments. Another emerging frontier of research is the role of magnetic fields in the evolution of nuclear clusters. While often overlooked due to their subtlety, magnetic fields can influence how gas collapses, how angular momentum is distributed, and how jets and outflows shape the immediate surroundings. There is growing evidence that in clusters with active galactic nuclei, magnetically driven winds may regulate star formation and impact the accretion dynamics of central black holes. This connects the study of nuclear clusters to the broader cosmic narrative of feedback mechanisms, the ways in which massive stars, supernovae, and active nuclei regulate their own growth and the evolution of their host galaxy. Nuclear star clusters, due to their position at the gravitational and dynamical center, are at the heart of this feedback loop. Feedback is not just theoretical, it's observable. In some galaxies, we see gas outflows and ionized emission lines indicating active starburst-driven winds within the nucleus. These winds can either blow gas out of the central region, suppressing future star formation, or they can compress nearby gas, potentially igniting new bursts. This self-regulating cycle mirrors the same starburst/feedback dynamic seen in larger galactic structures, but compressed into a tiny, dense, high-energy core. All of this contributes to the remarkable realization that nuclear star clusters are microcosms of galaxy formation, a scaled-down, accelerated version of the grand cosmic dance. Studying them gives us insight not only into the heart of individual galaxies but also into the broader rules that govern galactic structure across billions of light-years. Even their distribution across galaxy types is instructive. While nuclear star clusters are common in late-type spiral and dwarf elliptical galaxies, they are relatively rare in massive elliptical galaxies. In those giants, supermassive black holes tend to dominate the nucleus, and nuclear clusters are either absent or have been disrupted during major mergers. This implies that as galaxies grow in mass and complexity, their nuclear regions transition from stellar-dominated to black hole-dominated configurations. But this is not a clean, linear progression. Some massive galaxies still retain nuclear star clusters. Others, expected to host such clusters based on mass and morphology, don't. There are exceptions to every trend, hinting at the chaotic nature of cosmic evolution. Interactions, mergers, gas flows, internal dynamics, and even dark matter substructure can all alter the expected pathway. In this sense, nuclear star clusters are also probing the stochastic nature of galaxy formation, revealing that not all galaxies follow the same script, even if they play on the same stage. From the tiniest dwarf spheroidals to the grand spirals and CD galaxies at cluster centers, the presence, absence, or nature of a nuclear cluster tells a story. It is a fingerprint of the galaxy's past, a fossil record left behind in stars, gas, and gravitational binding. And despite their importance, these clusters are remarkably difficult to study. Because they sit in the bright, crowded centers of galaxies, separating light from individual stars can be extraordinarily challenging. It requires instruments with both high angular resolution and high contrast imaging capabilities. Ground-based telescopes now use adaptive optics to correct for atmospheric distortion, allowing astronomers to resolve stars just a few thousandths of an arc-second apart. Meanwhile, space-based observatories like the James Webb Space Telescope, JWST, and the Hubble Space Telescope offer unobstructed views of distant galactic cores, bringing even the faintest clusters into focus. With JWST now operational, astronomers are planning unprecedented studies of nuclear star clusters and high-redshift galaxies, those from the early universe. These observations may reveal the very first nuclear clusters ever formed, helping to answer long-standing questions about whether nuclear star clusters formed before or after the galaxies themselves. Imagine peering back in time, 10 or 12 billion years, and watching as the first dense knot of stars collapses at the center of a protogalaxy. Does it appear before the disk? Is it seeded by the first supernovae? Does it ignite a black hole, or does a black hole bring it into being? These are the kinds of questions we may soon be able to answer, not with speculation, but with data. And yet, for all we will learn, nuclear star clusters will still retain their mystery. Because beyond the light, beyond the gravity, beyond the data and equations, there is something deeply profound about these stellar hearts. They are not just structures. They are stories, compact, luminous, living stories of formation and destruction, of collision and coalescence, of evolution and entropy. They are proof that even in the most chaotic, violent corners of the universe, order can arise, that gravity can carve harmony out of mayhem, that matter can gather into brilliance, and that amidst the darkness of interstellar space, there are places where light is never absent. A place where a billion suns burn, packed tighter than anywhere else in the sky. A place where the laws of physics are tested every second. A place where the past of the galaxy, and perhaps its future, is quietly written in the orbits of stars. This is the mystery of nuclear star clusters. This is their legacy. And this is why we continue to study them. Not just to understand the universe, but to understand how complexity, beauty, and time itself can be crystallized into a single, radiant point in space. Yet, even as we peer deeper into the luminous core of nuclear star clusters, the questions become ever more intricate. It's as though, for every veil we lift, two more take its place. One such veil lies in the realm of stellar collisions, a natural consequence of the extreme densities in these regions. When stars are packed millions to a cubic parsec, as they are in the densest cores of nuclear clusters, the average distance between stars shrinks drastically. The result? A breeding ground for close encounters, tidal interactions, and even direct impacts. In these environments, stellar collisions are not rare cosmic accidents, they are inevitable. Over millions of years, stars can pass close enough to gravitationally interact, spinning each other up or stripping away their outer envelopes. In more extreme cases, they may merge entirely, creating objects like blue stragglers, massive, anomalously young-looking stars that stand out against their more evolved neighbors. These blue stragglers are particularly interesting because they offer a living record of past collisions, especially in older clusters where massive stars should no longer exist. Their presence hints at a hidden violence, a history of chaotic encounters, gravitational near-misses, and disrupted binaries. Moreover, these collisions may help build up unusually massive stars that later collapse into stellar mass black holes, feeding the cluster's population of compact remnants. And where there are black holes, there are bound to be cataclysmic events. In nuclear star clusters, the high density of stars and black holes also makes the region ripe for extreme mass ratio and spirals, MRIs, gravitational interactions where a stellar mass object, like a black hole or neutron star, spirals into a much more massive central black hole over many orbits. These spirals emit gravitational waves over a long period and are one of the prime targets for future missions like LISA. EMRIs are important not just because of the gravitational waves they emit, but because they allow us to map the spacetime around black holes with extraordinary precision. Each orbit is a probe, a tracer of the warping of time and space caused by the central mass. From these signals, we can reconstruct the spin, mass, and even the geometry of the black hole, offering one of the most precise tests of general relativity ever conceived. But EMRIs don't happen in isolation. Their formation depends on the complex dynamical interactions within the cluster, on how stars, black holes, and binaries scatter and exchange energy. In this sense, the structure of a nuclear star cluster is like a vast pinball machine, with every particle influencing the trajectories of others through chaotic gravitational kicks. In some simulations, these interactions can lead to the formation of hierarchical triples, systems where a tight inner binary is orbited by a third star or black hole. These configurations can induce quasi-Lyautov oscillations, periodically pumping up the eccentricity of the inner binary's orbit until the pair collides or merges. These mechanisms, triggered by the very structure of the nuclear cluster, may explain a significant fraction of black hole mergers observed by detectors like LIGO and Virgo. And let us not forget the role of gas. While nuclear star clusters are often treated as purely stellar systems, many retain or accrete significant amounts of gas, either from internal mass loss, e.g., red giants shedding their envelopes, or from external sources, e.g., gas inflow along galactic filaments. This gas isn't idle. It cools, collapses, and forms stars, creating new generations of stellar populations. The result is a multi-generational, chemically diverse population, where stars of different ages and metallicities coexist in tight proximity. By studying their spectra, we can reconstruct the chemical evolution of the cluster, learning when gas inflow occurred, how efficiently stars formed, and how stellar feedback enriched the surrounding material. Interestingly, in some nuclear clusters, we find anti-correlations between certain elements. For example, stars enriched in sodium often show lower levels of oxygen. This is a pattern seen in globular clusters as well, and may point to shared origins or similar enrichment processes. It raises the question, are nuclear clusters just supermassive globular clusters, or do they represent a fundamentally different class of object? The distinction is still debated. Some researchers argue that ultra-compact dwarf galaxies and nuclear clusters may represent stripped remnants of larger galaxies, galactic nuclei left behind after their outer regions were shredded by tidal forces. If true, this would mean that some nuclear clusters are not just the hearts of their own galaxies, but fossils of galaxies that no longer exist. Others suggest that globular clusters and nuclear clusters exist on a continuum, with nuclear clusters simply representing the extreme end of a mass density scale. What sets them apart, then, is not their formation mechanism but their evolutionary path, the environments in which they live, the interactions they experience, and the central black holes they may or may not host. Speaking of interactions, nuclear star clusters are often at the crossroads of galactic evolution. As galaxies merge and interact, their nuclei are among the first regions to feel the effects. Gas gets funneled inward, stars are dynamically heated or ejected, and the central structure can be completely reshaped. In some mergers, the nuclear clusters of both galaxies may survive the initial encounter, only to spiral together later and merge into a larger, more massive cluster, a process known as nuclear coalescence. This kind of coalescence can lead to a burst of new star formation, as gas clouds collide and compress, followed by a rapid quenching as feedback mechanisms take over. The newly formed nuclear cluster may bear the chemical signatures of both progenitors, a complex chemical mosaic that reflects the violent history of its creation. The gravitational interplay is just as dramatic. In some scenarios, a binary black hole may form in the nucleus as a result of a galactic merger. This binary interacts with surrounding stars, flinging them out of the nucleus and creating a core collapse structure with a sharp decrease in stellar density at the center. If the black holes merge, they may eject the surrounding stars in a gravitational recoil, temporarily emptying the nuclear region and leading to a phase of rebuilding. All of this shows that nuclear star clusters are not static. They are living, evolving systems, shaped by the tides of cosmic time. They form, grow, suffer disruption, rebuild, and occasionally even die. And in their deaths, they seed the next generation of structures, whether it's a supermassive black hole, a new starburst, or a compact galaxy nucleus hurtling through intergalactic space. And what of the future? With instruments like JWST, ELT, Extremely Large Telescope, and LISA on the horizon, we are entering a golden era for nuclear star cluster science. Soon, we may be able to track individual stars and extragalactic nuclei, detect gravitational waves from within clusters, and measure the masses of black holes down to the thousands of solar mass scale. These advances will allow us to answer fundamental questions about the origin of galaxies, the growth of black holes, and the interplay between dark matter and baryonic matter in the densest environments known. Perhaps even more tantalizing, we may begin to understand how common Earth-like conditions are within or near these clusters. Could dense clusters support stable planetary systems? Could life survive the harsh radiation fields? Could civilizations rise and fall in these regions, far different from our quiet solar neighborhood? These questions stretch the imagination, but they're grounded in real physics. And in a universe teeming with billions of galaxies, each with its own nuclear star cluster, the possibilities are as vast as they are humbling. Ultimately, the study of nuclear star clusters reminds us that the cosmos is a story of emergence. From the chaotic jostling of particles in the early universe, to the majestic spirals of galaxies, to the silent brilliance of clusters packed with a billion stars, we see order arise from disorder, pattern from noise, beauty from entropy. And nestled at the center of that beauty is a cluster of stars, quiet, brilliant, ancient, and eternal. But even as we marvel at the grandeur of nuclear star clusters, those luminous hearts beating at the core of galaxies, there's one truth we cannot ignore: we are only beginning to scratch the surface of their complexity. Every new observation, every simulation, every spectrum adds a fragment to the puzzle, but the full picture remains elusive. One of the most profound questions that nuclear star clusters pose relates to their relationship with dark matter. While these clusters are typically dominated by baryonic, normal, matter in the very central regions, their formation and evolution are undoubtedly influenced by the dark matter halos of their host galaxies. In low-mass galaxies, where the dark matter core may be cuspy or chord, the density profile of dark matter can dramatically influence how stars migrate inward or how gas is retained for star formation. This interaction may even leave detectable signatures. For instance, flattened or triaxial structures in the nuclear region can hint at the underlying gravitational potential shaped by both dark and luminous mass. Moreover, if nuclear star clusters form via inspiraling globular clusters, dragged inward by dynamical friction, then their journey is shaped by the dark matter density profile. A core-like halo may slow their infall, a cuspy profile accelerates it. Thus, the very existence or absence of a nuclear cluster in certain dwarf galaxies could serve as an indirect probe of the nature of dark matter itself. And what of exotic compact objects in these clusters? Nuclear star clusters are prime environments to search for unusual end states of stellar evolution: primordial black holes, boson stars, or dark matter clumps. The gravitational potential at the center of these clusters is steep enough to host rare objects that might never form in isolation. If such exotic bodies exist, their effects might be felt in the dynamical heating of the cluster, or in the subtle distortions of stellar orbits, or even in unusual electromagnetic transients that don't fit neatly into known categories. Such possibilities fuel speculative but exciting research. What if some nuclear star clusters host not only conventional stellar remnants, but strange matter objects, hypothetical quark stars composed of up, down, and strange quarks? Could these be detected through sudden, unexplained glitches in timing data, or by their unusually hard X-ray emission? These questions may seem fantastical, but they are grounded in astrophysics. Nuclear star clusters, because of their density, age, and gravitational depth, are natural laboratories for high-energy physics and compact object astrophysics. Indeed, the potential for surprises is perhaps the most thrilling aspect of studying these clusters. Time and again, they have challenged assumptions about how galaxies grow, how stars evolve in extreme environments, how black holes form, and how feedback regulates star formation. And then, there's the matter of cosmic time. Nuclear star clusters are not ephemeral features. They are ancient. Some have been around since the earliest epochs of galaxy formation. They have seen their host galaxies change shape, interact with neighbors, absorb companions, and accrete gas. Some have survived supernova bombardments, tidal distortions, and even close brushes with central black holes. This longevity makes them not just stellar systems, but cosmic witnesses. A nuclear star cluster that exists today may have been born when the universe was less than 1 billion years old. It may have orbited through a protogalactic disk, fallen inward via dynamical friction, accreted stars from the bulge, and now sits serenely in the core of a mature spiral galaxy. Its stars tell the story, not in words, but in chemical signatures, kinematic trails, and stellar populations etched across eons. These stories can be read through multi-wavelength observations. Ultraviolet imaging reveals the youngest, hottest stars, evidence of recent star formation. Infrared peeks through dust to show the older, redder populations. Optical data gives us velocity dispersions and structural parameters. X-rays uncover compact binaries, supernova remnants, and possible accreting black holes. Even radio observations contribute, revealing masers, jet interactions, or low-level AGN activity. By combining all these data, astronomers are assembling a holistic picture of nuclear star clusters, a portrait composed of dozens of layers, each corresponding to a different physical process, epoch, or component. And yet, for all this progress, some clusters remain enigmatic. There are nuclear clusters with off-center positions, sitting slightly askew from the galactic photometric center. This raises questions about whether they are dynamically relaxed, or whether gravitational interactions are still playing out. Others display double nuclei, suggesting either ongoing mergers or binary cluster systems in mid-coalescence. Some nuclear clusters even seem to show evidence of counter-rotation, where two stellar populations orbit in opposite directions. This is strong evidence for multiple formation episodes, possibly involving accreted gas with a different angular momentum vector than the pre-existing stars. It shows that nuclear star clusters are not simple structures. They are layered, dynamic, and sometimes paradoxical. Their study, therefore, requires not just better data, but better models, sophisticated simulations that include gravity, gas dynamics, star formation, feedback, magnetohydrodynamics, and radiation transport. In recent years, high-resolution simulations have begun to shed light on how nuclear clusters grow, evolve, and sometimes dissolve under the influence of tidal stripping or feedback-induced outflows. One especially promising line of research involves zoom-in cosmological simulations, models that track the formation of galaxies from the early universe to today, but with enough resolution to resolve the nuclear regions. These simulations are showing how gas-rich mergers, bar-driven inflows, and central starbursts can all contribute to building dense stellar nuclei. The simulations also highlight the role of metallicity and stellar feedback. In metal-poor environments, gas cools less efficiently, leading to more gradual and extended star formation. In contrast, metal-rich gas can fragment quickly, creating compact, dense clusters with complex internal dynamics. Feedback from massive stars, via winds, radiation, and supernovae, can regulate the size, shape, and survivability of these nuclear regions. Even the interplay between rotation and pressure support within the cluster can vary widely. Some nuclear clusters are rotation-dominated, more like mini-galactic disks. Others are pressure-supported, akin to elliptical galaxies. Some show signs of flattening, others are nearly spherical. This structural diversity is another sign that nuclear clusters do not form in a single way. Rather, they are shaped by a multitude of processes, each influenced by the specific conditions of their host galaxy. And as our observational tools grow more powerful, we may begin to discover nuclear clusters in unusual places, in ultra-faint dwarf galaxies, in isolated ellipticals, or even in tidal debris fields. Each discovery will expand the boundaries of our understanding, forcing new models, raising new questions, and possibly revealing new kinds of objects that straddle the line between star cluster and galaxy nucleus. Perhaps one day we will detect a wandering nuclear cluster, a remnant core flung into intergalactic space after a galactic merger. Perhaps we'll find clusters forming today in galaxies undergoing rapid transformation. Or perhaps we'll identify dark clusters, nuclear regions dominated by black holes and neutron stars, invisible to light but detectable through gravitational lensing or stellar motions. Whatever we find, nuclear star clusters will continue to challenge and inspire. They remind us that even in the most familiar structures, galaxies with bright centers, old stars, quiet bulges, there is mystery. There is dynamism. There is evolution playing out over 1 billion years, in the quiet ticking of orbital paths, in the slow fusion of hydrogen in red giants, and in the sudden flare of a supernova that enriches the next generation. These clusters are cathedrals of time. They are relics of cosmic dawn and survivors of cosmic upheaval. And they may yet be the key to unlocking the deepest questions we have about our universe. What came first, stars or black holes? How do galaxies grow and regulate themselves? What is the nature of dark matter? And how do order and complexity emerge from chaos? To answer these questions, we look to the centers of galaxies, to the most densely packed systems in the cosmos, to the glowing cores where past and future converge. We look to nuclear star clusters, and we listen to what they have to say. And so we continue, deeper still, into the heart of these mysterious stellar metropolises, where time stretches and light struggles to escape the pull of the immense. If nuclear star clusters are the custodians of galactic memory, then we must turn to their motions, the precise dance of stars within them, to read the long-forgotten stories carved by gravity itself. Stellar kinematics, the measurement of how stars move in these clusters, has become a cornerstone of nuclear star cluster research. With advanced instruments capable of resolving the light of individual stars, especially in the nearby galaxies like our own or M31, astronomers can now map the velocity dispersions and rotational profiles of thousands of stars in and around a nuclear cluster. What they find is often astonishing. In some nuclear clusters, the stars swirl in organized, disk-like rotations, hinting at a history of gas accretion and in situ star formation. In others, the motion is more chaotic, indicating that stellar migration, perhaps from globular clusters falling inward, has played a larger role. Many nuclear clusters actually show multi-component kinematics, an inner, fast-rotating disk and an outer, pressure-supported spheroid. This duality is a key fingerprint of multiphase formation, with each component preserving the angular momentum of the gas or stars from which it originated. And within that motion, there's often something darker hidden, a central black hole. While nuclear star clusters and supermassive black holes were once thought to be mutually exclusive, we now know that they can, and often do, coexist. In fact, galaxies like the Milky Way host both. Our central nuclear star cluster, spanning several parsecs and weighing millions of solar masses, surrounds a 4 million solar mass black hole, Sagittarius A. Detecting black holes in other nuclear clusters is harder, especially in distant galaxies. But with adaptive optics, precise radial velocity measurements, and high-resolution imaging, astronomers can observe the motions of stars near the very center of these clusters. A rise in velocity dispersion at the core, an otherwise unexpected increase in stellar speeds, can betray the presence of a compact, invisible mass. And when combined with stellar population models and dynamical simulations, these kinematic spikes often point to one thing: a black hole. The implications of this coexistence are profound. It suggests that nuclear star clusters and black holes might form together, possibly through a combination of stellar accretion and gas inflow. Some models even propose a coevolution scenario, where nuclear clusters act as seed environments for growing black holes, which in turn regulate the growth of the cluster through feedback. Alternatively, it could be that black holes form first, shaping the potential well into which stars later migrate. This chicken or egg problem, what comes first, the black hole or the cluster, is one of the great unsolved questions in galactic astronomy. And it's not just academic, it has ripple effects on our understanding of galaxy formation, AGN evolution, and even reionization in the early universe. Another layer of complexity arises when considering the intermediate mass black holes, IMBHs, those mysterious objects with masses between 100 and 100,000 solar masses. IMBHs have long been theorized as possible missing links between stellar mass black holes and the supermassive giants at galactic centers. Nuclear star clusters, with their dense stellar cores and potential for runaway mergers, are prime environments for forming IMBHs. Imagine this. In the early stages of cluster evolution, before massive stars have time to go supernova, they might collide and merge rapidly in the center. This runaway collision scenario could give birth to a massive star, hundreds of solar masses, which might collapse directly into an IMBH. Alternatively, repeated mergers of black holes could gradually build up a central object of intermediate mass, especially in clusters where dynamical friction concentrates the heaviest remnants in the core. Detecting IMBHs is no simple task. Their gravitational influence is subtle, and they rarely emit strong signals unless they're accreting gas or involved in a merger. However, careful studies of nuclear star clusters, looking for stellar velocity dispersion anomalies, X-ray flares, or even gravitational waves, may eventually reveal their presence. Indeed, the gravitational waves produced by IMBH mergers, or by IMBHs capturing and consuming stellar mass black holes, could be detectable by LISA in the near future. This would open a new window into cluster dynamics and black hole growth, allowing us to see events hidden behind thick veils of dust and light. But even as we search for black holes and trace stellar paths, there's a more human question looming in the silence of these star-packed cities. Could planets exist here? Could life arise in a nuclear star cluster? At first glance, the answer seems like an emphatic no. The radiation environment is harsh. The stellar density is immense, comparable to packing millions of stars into a space no larger than a few light years. Close encounters between stars can strip away planets, destabilize orbits, or bathe systems in high-energy radiation from nearby supernovae. But recent studies suggest that under the right conditions, planetary systems can survive, even thrive, in dense clusters. The key is orbital stability. If planets orbit very close to their host stars, within 1 or 2 AU, they are more likely to remain bound even during close stellar flybys. Moreover, some stars might migrate inward from less dense regions, bringing planets with them into the nuclear region. What's more intriguing is the possibility that such planets could experience frequent close encounters with other stars, potentially even passing near habitable zone planets orbiting different suns. This raises wild possibilities for interstellar panspermia, the transfer of life-bearing materials from one planetary system to another, facilitated by the gravitational chaos of a densely packed stellar core. In such a scenario, nuclear star clusters might not only host planets, but act as incubators of complex chemistry, or even life exchange hubs between planetary systems. Of course, all this is speculative. But as we learn more about exoplanets, especially in dense environments like globular clusters, it's not unreasonable to extend those ideas into the even more extreme context of nuclear clusters. And then there's the final, poetic irony. For all their brilliance, for all their history and violence and quiet dignity, nuclear star clusters are often invisible to us. In distant galaxies, they vanish into the glare of the central bulge, hidden by dust or confused with the light of active galactic nuclei. In others, they are misidentified as compact ellipticals, or overlooked entirely due to resolution limits. Yet they are everywhere. Estimates suggest that over 70% of galaxies, especially those with masses below a few billion solar masses, host nuclear star clusters. That's billions upon billions of galactic hearts, glowing quietly at the center of spinning star cities, each one telling a different story. Stories of collapse and birth, of mergers and solitude, of black holes growing in silence, and of stars crowding together in the dark. And in every one of them lies a paradox, a place of both creation and destruction, of order and chaos, of eternity and impermanence. We gaze at these hearts from across millions of light years, trying to decode their secrets with our telescopes, our simulations, and our minds. And with every photon we capture, we get closer, not just to understanding them, but to understanding ourselves. why galaxies form the way they do, why stars are born where they are, and what cosmic forces shape the cradle of our own existence. For we, too, live in a galaxy with a nuclear star cluster. And we, too, are part of its story. And in continuing this journey to understand the deep cosmic architecture of nuclear star clusters, we must finally confront the most speculative, the most frontier-pushing domain of inquiry: how these clusters tie into the fate of galaxies, and possibly, the ultimate destiny of matter and structure in the universe. To fully grasp their significance, consider that nuclear star clusters are cosmic endpoints, the densest places where normal matter settles over billions of years. They are gravitational wells into which stars migrate, gas accumulates, and energy is exchanged. In many respects, they are entropy engines, systems slowly relaxing toward equilibrium in a universe moving inexorably toward disorder. But this isn't a quiet process, it's full of drama. As galaxies interact, merge, and cannibalize one another, the dynamical fates of their nuclear clusters become entangled. In major galactic mergers, two supermassive black holes can form a binary and eventually coalesce. But what happens to their surrounding nuclear clusters? Simulations show that these clusters can merge themselves, forming even more massive, complex nuclei. Or, if disrupted, they can shed stars into the galactic halo, seeding it with ancient populations and creating a fossil record of past galactic interactions. Some clusters, especially in dense galaxy clusters or interacting systems, are even ripped entirely from their hosts, becoming ultra-compact dwarf galaxies (UCDs). These are objects that blur the line between globular clusters, nuclear clusters, and stripped galactic cores. Some UCDs, like M60 UCD1, are believed to be the former nuclei of galaxies long since destroyed by tidal forces. And what's more stunning, these stripped remnants still harbor massive black holes, far larger than expected for objects their current size. This discovery leads us to an extraordinary implication. Nuclear star clusters are not just anchors of galaxies, but potentially survivors of galactic death. They may outlast their host galaxies entirely, floating as stellar fossils through intergalactic space, carrying within them the gravitational signature of their long-lost homes. Like ghosts with memory, they drift, dense, ancient, and impenetrably silent. And perhaps, if one day in the far future the galaxies themselves dim, and star formation ceases, and all that remains are the last red dwarfs slowly burning out in the cold dark, nuclear star clusters may be among the last visible structures. They will have long since stopped forming stars. Their brightest inhabitants will have gone supernova or collapsed into white dwarfs, neutron stars, and black holes. But bound by gravity, these remnants will continue orbiting each other for eons, perhaps trillions of years, until gravitational perturbations and eventual quantum effects dissolve them. But let's pull back to the present. There is still much we don't know, still mysteries unresolved, still observations out of reach. Even the exact scaling relations between nuclear star clusters and their host galaxies are not fully understood. The famous M-sigma relation, linking supermassive black hole mass to the velocity dispersion of the host galaxy's bulge, has a nuclear star cluster analog, but it's far more scattered, complex, and dependent on galaxy morphology and evolutionary history. In spiral galaxies, especially those with pseudobulges, nuclear star clusters are often far more dominant than black holes. In elliptical galaxies, it's usually the opposite. And yet, in low-mass galaxies, where black holes are harder to form and retain, nuclear star clusters are ubiquitous. This gives rise to one of the field's most compelling hypotheses, that there is a mass threshold below which star clusters dominate, and above which black holes dominate. Perhaps the processes that form nuclear clusters are suppressed once a black hole passes a certain mass, because feedback from accretion heats the gas, preventing further in situ star formation. In this view, nuclear star clusters and central black holes are two outcomes of the same centralization process, driven by galaxy evolution, gas dynamics, and feedback. It's not necessarily one or the other, but a continuum, shaped by initial conditions, merger history, and cosmic environment. This theory continues to be tested by observations of nucleated dwarf galaxies, which offer perhaps the clearest look at nuclear star cluster formation in isolation. These tiny galaxies, some with just a few 100 million stars, often host surprisingly massive clusters at their cores. Their simplicity, compared to large spirals or ellipticals, makes them ideal laboratories for disentangling the competing theories. Did the cluster form from globular cluster migration, or from central starbursts? Was it shaped by dark matter, or baryonic collapse? The upcoming generation of telescopes, such as the Extremely Large Telescope, ELT, 30-meter telescope, TMT, and James Webb Space Telescope, JWST, are already beginning to provide clearer answers. JWST's infrared capabilities, in particular, can peer through dust and resolve nuclear regions in distant galaxies at high redshifts. For the first time, we are glimpsing nuclear star cluster analogs in the early universe, when galaxies were still clumpy, turbulent, and gas-rich. Already, there are hints of compact central starbursts forming at Z4 to 6, dense knots of stars that could evolve into modern-day nuclear clusters. By tracing their evolution over cosmic time, we can see whether these objects survive, merge, or fade, adding vital data to the story of how galactic nuclei form and evolve. Moreover, with spectroscopic instruments capable of determining chemical abundances of individual stars, we're now seeing multiple stellar populations in nuclear clusters, just as we do in globular clusters. This supports a history of episodic star formation, often punctuated by periods of intense activity followed by quiescence. These cycles are often driven by gas inflow from the galactic disk, sometimes channeled inward by bars, tidal torques, or interactions. The infalling gas cools, collapses, and forms a new generation of stars, sometimes mixing with older populations but often remaining distinct. Over time, these layers build up like the rings of a tree, telling the cluster's history in age gradients, metallicity differences, and kinematic signatures. This leads to one of the most awe-inspiring realizations about nuclear star clusters. They are time machines. They don't just form stars, they record time. Every age difference, every chemical fingerprint, every subpopulation encodes the conditions of the galaxy at the time of formation. They are, in a very real sense, fossil archives of galactic history. And perhaps the greatest frontier now lies in connecting these local observations to cosmological context. How do nuclear clusters in nearby galaxies compare to those at cosmic dawn? Do certain cluster properties correlate with large-scale structure, environment, or epoch? Are clusters in field galaxies different from those in groups or clusters? These are questions only long-term statistical surveys can answer. To that end, missions like ELSSD, Euclid, and Nancy Grace Roman Space Telescope are expected to catalog millions of galaxies across cosmic time, providing unprecedented datasets to link structure, morphology, and nuclear content. As machine learning and AI-driven data mining become more refined, patterns may emerge that were previously buried in noise. And one day, perhaps sooner than we think, we may reach a point where we can model the entire life cycle of a nuclear star cluster, from its first stars to its ultimate fate, using physics, observations, and simulations in harmony. That moment will be a triumph not just of astronomy, but of human curiosity. For what drives our fascination with these clusters? Why do we gaze into their crowded, glowing hearts? It is because they mirror ourselves. They are gatherings of individuals into a larger whole, complex, layered, always changing. They are defined not by one star, but by the interplay of thousands, just as we are defined not by one moment, but by the convergence of many. They are both chaotic and ordered, violent and serene, ancient and alive. They are, in their own cosmic way, communities of stars, singing a song of gravity and light, over billions of years. And in listening to that song, we learn not only what they are, but who we are, and where we are, in this vast, ancient, and still unfolding universe. And so, as we reach into the furthest depths of cosmic understanding, we find that nuclear star clusters aren't just isolated structures, they are nodes in a vast galactic network. Each one is a gravitational summation of a galaxy's lifetime, a deeply encoded result of billions of years of mergers, star formation, interactions, collapses, and silent cosmic arithmetic. But to truly appreciate their scale and role in the universe, we must explore how they might contribute to cosmic evolution itself. In cosmological simulations, large-scale structure emerges as dark matter collapses into filaments and halos, pulling ordinary matter along with it. Galaxies form at the centers of these halos, and inside them, stars are born. But galaxies themselves are not isolated. They evolve through interactions, mergers both major and minor, gravitational harassment, and tidal stripping. Every time a dwarf galaxy falls into a larger host, it is shredded by the gravitational tides, its stars dispersed into streams, its gas stripped, and most crucially its nuclear star cluster is often left intact. This brings us to the concept of nuclear star cluster cannibalism. These clusters, compact and dense, are the most gravitationally bound parts of their original galaxies. When the outer galaxy is disrupted, the cluster survives, now an intruder in a new host. It may wander the galaxy halo, or, through dynamical friction, slowly spiral toward the center of its new host and merge with the existing nuclear cluster. Over time, a massive, complex nuclear star cluster can form, not from a single event, but through the accretion of many such ancient remnants, each one a relic of a consumed galaxy. This process is supported by observations. In the Milky Way, and in other large galaxies, some stars within nuclear clusters show properties inconsistent with in situ formation, hinting at an ex situ origin, brought in from elsewhere, long ago. These immigrant stars often have unusual chemical abundances or kinematics. And in galaxies where clusters appear to be off-center or elongated, simulations suggest we are witnessing a merger in progress. Thus, nuclear star clusters become archives of galactic cannibalism, storing within them the story of hierarchical growth, one galactic meal at a time. This is consistent with lambda-CDM cosmology, in which structure forms from the bottom up, small things merge to form larger ones. It is entirely possible that the nuclear star cluster at the heart of the Milky Way is composed of the cores of long-lost dwarf galaxies, each one now no more than a few stars orbiting in a silent dance. And some of those stars may have once had planets, life, even civilizations, now swallowed by the Milky Way, remembered only in the orbital parameters of the nuclear cluster. As poetic as this sounds, there is growing observational evidence for this idea. The Andromeda Galaxy, for example, has a nuclear cluster with a double nucleus, two brightness peaks separated by a few light-years, connected by a disk of stars. This structure may result from a recent merger of two nuclear clusters, or from a lopsided distribution of stars orbiting a central black hole. Either way, it tells us that nuclei can be dynamic and violent places, not static centers. And beyond dynamics and mergers, there is also the question of environmental influence. Galaxies don't evolve in a vacuum, literally and metaphorically. In dense clusters of galaxies, like the Virgo or Coma clusters, galaxies are exposed to harassment, rapid encounters with other galaxies, ram pressure stripping by the hot intracluster medium, and tidal interactions that can disturb their structure. In these environments, central gas inflows can be enhanced or suppressed, changing the conditions under which nuclear clusters form. In low-density environments, like the field or voids, galaxies evolve more slowly, with less disruption. Here, secular processes like bar-driven inflows and internal instabilities may dominate the formation of nuclear clusters. Thus, by comparing nuclear clusters across environments, we can gain insight into how cosmic context shapes central structure. Another layer of complexity is added by the influence of dark matter. While dark matter doesn't interact electromagnetically, it dominates the gravitational potential of galaxies, especially in their outskirts. But its influence can extend to the center, particularly in low-mass galaxies where baryons don't dominate. Some models suggest that dark matter cusps could aid in the concentration of gas into the center, triggering star formation and cluster growth. Others suggest that core formation via feedback, stellar winds and supernovae pushing back against inflow, can suppress nuclear cluster formation. This leads to an interesting tension. In some galaxies, dark matter may enable nuclear cluster formation. In others, it may prevent it. The answer likely lies in the balance between inflow timescales, star formation efficiency, and feedback strength, a balance we are still striving to model with high precision. And then there is the theoretical possibility that dark matter itself could accumulate in nuclear clusters. Though it interacts only via gravity, dense regions like nuclear clusters may act as gravitational traps for dark matter particles. Some exotic models propose that dark matter could decay or annihilate in such dense environments, producing detectable gamma rays or other signals. In this sense, nuclear clusters may serve not only as laboratories for baryonic astrophysics, but for fundamental particle physics as well. Indeed, the dense environments of nuclear clusters are being considered as potential sources of high-energy phenomena, including gamma-ray bursts, supernovae, and even gravitational wave sources. The extreme stellar densities and high rates of close encounters can lead to the formation of tight binary systems, collisions, and compact object mergers, all of which produce energetic events. For example, compact binaries, such as white dwarf, neutron star pairs, double black holes, or white dwarf mergers, are more likely to form in environments like nuclear clusters due to enhanced stellar interactions. These systems are prime candidates for gravitational wave emission, and their eventual merger may produce short gamma-ray bursts, kilonovae, or type Ia supernovae. This positions nuclear clusters as potential engines of cosmic fireworks, sending out gravitational ripples or flashes of light across the cosmos, events we can detect and trace back to their dense, star-packed origins. All of this brings us to a startling realization. Nuclear star clusters are not just astrophysical curiosities. They are central players in galactic evolution, in cosmic structure formation, and possibly in fundamental physics. They are places where ordinary matter meets extreme physics, where gravity shapes light, and where time and history are written in stars. And in that sense, perhaps nuclear star clusters are more than just dense collections of stars. They are microcosms of the universe, structured, layered, evolving, mysterious. They remind us that even in the darkest corners of galaxies, light persists, not just metaphorically, but literally. Trapped in orbits, compressed in binaries, ejected in nova bursts, absorbed by black holes, light traces every moment of the cluster's history. As our instruments grow more powerful, as our simulations more detailed, and our understanding more nuanced, we will continue to uncover the secrets of these cosmic hearts. They will teach us not just how galaxies live, but how they remember. And how, in the final tally of the universe's story, even the smallest, most compact spaces can contain the vastest truths. And now, as we plunge deeper into the legacy and future of nuclear star clusters, we reach perhaps the most profound realization. These compact structures, often no more than a few parsecs wide, may contain the clearest evolutionary signature of the cosmic dance between matter, gravity, and time. They are not merely results of astrophysical processes. They are reflections of them, compact mirrors held up to the face of the universe itself. Let us return briefly to the Milky Way, for here we can study a nuclear star cluster in detail unlike anywhere else. The galactic center contains a nuclear star cluster with a mass of about 20 million solar masses. It is incredibly dense, with stars packed so tightly that collisions and interactions are common on cosmic timescales. Surrounding it all is Sagittarius A, the supermassive black hole of about 4 million solar masses, quietly lurking at the heart of this dense stellar congregation. What makes the Milky Way's nuclear star cluster so unique is that it has been observed across the entire electromagnetic spectrum, from X-rays and infrared to radio. Adaptive optics and infrared observations have allowed astronomers to track the individual orbits of stars around SGRA, most famously the star S2, whose 16-year orbit provided one of the strongest confirmations of the existence of a central black hole. But this ability to track individual stars has also allowed scientists to map the structure of the nuclear cluster in exquisite detail. It's not perfectly spherical, it's slightly flattened, with signs of rotation, and possibly even a stellar disk embedded within it. Some of the stars are incredibly young, just a few million years old, which is surprising, because the galactic center is a harsh environment for star formation. Tidal forces from the black hole, intense radiation, and turbulent gas should all suppress star birth. Yet, there they are, massive O and B-type stars, orbiting close to the monster at the center. This paradox has led to the hypothesis that star formation in nuclear clusters can occur under extreme conditions, possibly triggered by gas inflows during periods of disk instability or bar-driven funneling of material. Or perhaps these young stars formed elsewhere and migrated inward via dynamical friction, although their presence on short-period orbits makes this scenario less likely. Whatever the origin, their presence shows us that nuclear clusters are not just fossils. They are also living systems, still forming stars, still evolving, still active in the present day. Now scale this up across the observable universe. Every time we look at the center of a galaxy and see a bright point source, often unresolved in distant galaxies, we may be seeing a nuclear star cluster, shining like a jewel embedded in galactic darkness. In low-mass galaxies, these clusters can dominate the central light profile. In more massive galaxies, they often compete with or are entirely outshone by AGN, active galactic nuclei. But their coexistence with central black holes raises one of the most enduring and fascinating questions in extragalactic astrophysics. Which came first, nuclear star clusters or supermassive black holes? There is no simple answer. In some models, nuclear clusters form first through the migration of globular clusters or in situ star formation from gas inflows. Over time, the cluster becomes dense enough that stellar collisions and runaway mergers lead to the formation of an intermediate mass black hole, which then grows via accretion and becomes a supermassive black hole. In this picture, the nuclear cluster is the cradle of the black hole. In other models, supermassive black holes form early, seeded by direct collapse of massive gas clouds or the death of the universe's first stars. These black holes then influence their surroundings, regulating gas inflow, preventing further star formation, or even destroying nuclear clusters via energetic feedback. Here, the black hole is the ruler, and the nuclear cluster is secondary, allowed to exist only if the black hole permits. But the truth may lie somewhere in between. There may be different evolutionary paths depending on galaxy mass, merger history, and environmental factors. In low-mass galaxies, where black hole formation is inefficient, nuclear clusters may be dominant. In massive galaxies, the black hole may reign supreme. And in intermediate mass galaxies, like the Milky Way, both may coexist, interacting, evolving, and growing together in a gravitationally complex relationship. This idea of coevolution is gaining traction, especially as we uncover more evidence of feedback loops between nuclear clusters and black holes. For example, the growth of a black hole via gas accretion can heat and expel gas from the nucleus, temporarily halting star formation. But later, the cooled gas may fall back in, reigniting star birth and rebuilding the cluster. Thus, nuclear clusters and black holes may not just compete for resources. They may alternate in dominance, like shifting tides within the galactic core. Even more astonishing is the possibility that nuclear star clusters may seed the formation of black holes in other galaxies. As we observe dwarf galaxies and ultra-diffuse galaxies, we often find central clusters that appear to harbor intermediate mass black holes. These may represent an early stage in the evolutionary sequence, a snapshot of a process that eventually leads to the growth of the massive quasars we see in the early universe. Indeed, the most luminous quasars, powered by billion solar mass black holes less than a billion years after the Big Bang, pose a major challenge to astrophysics. How did such massive objects form so early? One possible path is through the rapid collapse and coalescence of dense nuclear star clusters in young galaxies. The gravitational potential in these regions, aided by gas infall and runaway mergers, could provide the right conditions for rapid black hole growth, perhaps explaining how these quasars emerged so quickly. And so, we return to the central idea: nuclear star clusters may be the missing link, the evolutionary stage that connects globular clusters, galaxy centers, and supermassive black holes. They are bridges between scales, between physical processes, and between epochs. The study of nuclear star clusters is not just about understanding a few exotic objects. It is about piecing together the grand narrative of structure in the universe. From the smallest dwarf galaxy to the largest cluster of galaxies, from the faintest stellar cluster to the brightest quasar, from the chaotic birth of stars to the quiet dance of ancient stellar remnants, everything is connected. And nuclear star clusters, glowing quietly at the centers of galaxies, are the cosmic punctuation marks that tell us when galaxies began, what they endured, and how they might end. They are not just clusters of stars. They are clusters of stories, written in light, bound by gravity, whispering across the cosmos to those who dare to listen. And still, the whispers of nuclear star clusters are far from fading. If anything, they're becoming louder with each new discovery, resonating across the disciplines of astrophysics, cosmology, and computational modeling. Because in their simplicity lies complexity, in their compactness, the unfolding of grand cosmic processes. As we look toward the next generation of observatories, nuclear star clusters are primed to take center stage in our understanding of the universe's deepest mechanisms. Instruments like the James Webb Space Telescope, JWST, with its unparalleled infrared capabilities, and the upcoming extremely large telescopes, ELTs, such as the 30-meter telescope, TMT, the European ELT, and the Giant Magellan Telescope, GMT, are set to peel back the layers of cosmic dust that obscure our view of galactic cores. These tools will allow us to resolve nuclear star clusters in distant galaxies, measure their stellar populations, dynamics, and even dissect their star formation histories with unprecedented clarity. This new era of observation opens the door to cosmic archaeology, the process of unraveling how many generations of stars have lived and died in these clusters. We will be able to determine chemical enrichment patterns, which act like fossil records of ancient supernova explosions. These patterns will tell us what kind of stars existed billions of years ago, how often they exploded, and how they seeded future generations of stars with heavy elements like carbon, oxygen, and iron. Even more intriguingly, there's the potential to detect intermediate mass black holes, IMBHs, hidden within nuclear star clusters. These elusive black holes, weighing in at 100 to 100,000 times the mass of our Sun, represent a missing rung in the black hole mass ladder. They're too big to form from normal stellar collapse and too small to be supermassive. Nuclear clusters, with their high stellar densities and deep gravitational wells, are some of the best places to look for them. The presence of an IMBH could significantly influence the dynamics of the cluster, causing stars to move faster than expected or producing hypervelocity stars ejected from the core. With future high-resolution spectroscopy and astrometric monitoring, we might detect these gravitational fingerprints and confirm the existence of these mysterious objects. And should we find them, it could finally fill a gap in our understanding of how supermassive black holes formed. Perhaps every giant black hole at the center of a galaxy once began as an IMBH in a dense nuclear cluster, growing slowly over billions of years through accretion and mergers. This would make nuclear clusters not just companions of black holes, but their cosmic nurseries. The implications stretch even further. With gravitational wave detectors such as LIGO, Virgo, CAGRA, and future space-based observatories like LISA, Laser Interferometer Space Antenna, we are now entering an era where we can hear the universe, not just see it. Nuclear star clusters, with their high rates of binary interactions and stellar collisions, are prime candidates for the production of compact object binaries, black hole pairs, neutron star pairs, or mixed systems. These objects, once tightly bound, can eventually spiral into each other and merge, releasing powerful gravitational waves that ripple across space-time. Nuclear clusters, because of their densities, dramatically increase the chances of these rare systems forming and surviving long enough to coalesce. In fact, some of the black hole merger events already detected by LIGO may have originated in dense stellar environments like nuclear clusters. Simulations show that in such environments, dynamical capture, where two black holes pass close enough to radiate energy via gravitational waves and become bound, can lead to mergers that wouldn't happen in more diffuse regions of the galaxy. This means that by studying nuclear star clusters, we are not only learning about galaxies, we are tracing the origins of space-time ripples themselves. And still, we must not forget the planetary implications. Though they are harsh environments for life as we know it, nuclear clusters raise tantalizing questions. Could planets form in such crowded regions? Could they survive? What would it be like to orbit a star surrounded on all sides by thousands of neighbors, all within a few light years? While planetary systems would be heavily perturbed by close stellar encounters, it's not out of the question that some may form in outer orbits or remain stable in binary systems. Such planets might be subjected to frequent cometary bombardments, fluctuating radiation, and gravitational tides. Yet, they would also experience a sky of incredible brilliance, stars visible in the day, 1,000 suns dancing overhead, casting shadows at night. And what if intelligent life evolved there? How would their science develop? Their myths? Their astronomy? Would a civilization in a nuclear cluster even know what a dark sky was? Would they ever see the cosmic microwave background? Would they even think they were in a galaxy, or would their vision be limited to the blinding swarm of local stars? These are speculative questions, yes, but they remind us that nuclear star clusters are not only astrophysical laboratories, they are philosophical frontiers. They ask us to reconsider what a galaxy is, what a star cluster is, and how the boundaries between them blur in the presence of extreme density, time, and dynamical evolution. They ask us to rethink formation, destruction, and rebirth, not just of stars, but of galaxies, black holes, and perhaps civilizations. And through it all, they continue to surprise us. Just recently, nuclear star clusters have been discovered in galaxies where they were not expected. Some ultra-diffuse galaxies, barely visible even to powerful telescopes, appear to host compact nuclei. Others show signs of off-center clusters, hinting at recent galactic mergers or gravitational instabilities. In some rare cases, nuclear clusters appear to have been ejected entirely, flung out of their host galaxies by complex gravitational interactions, especially in three-body systems involving multiple black holes or during recoil events following black hole mergers. These wandering nuclear clusters are cosmic orphans, dense, bright, and adrift in intergalactic space. If confirmed, they represent an entirely new class of objects, previously unimagined, the stripped cores of galaxies, cast adrift yet still burning with the light of ancient stars. Could some of these be the origins of ultra-compact dwarf galaxies, or even mistaken for globular clusters? The distinction grows thin, and the taxonomy of stellar systems begins to crumble. We are seeing not a neat evolutionary ladder, but a chaotic web of formation and transformation, where one object morphs into another through time, tidal forces, and the sheer randomness of cosmic events. In this way, nuclear star clusters become nodes in the cosmic web, not just gravitational centers, but informational ones. Their structure encodes data from the earliest epochs of galaxy formation. Their stars carry the chemical signatures of ancient supernovae. Their motions reflect the gravitational potential of their hosts. Their interactions produce gravitational waves. Their very existence tells us that in the hearts of galaxies, the universe never rests. And perhaps most importantly of all, they remind us that the center is not silent. At the heart of galaxies, where chaos reigns, where gravity sculpts time, where stars are born and die in crowded orbits, there lies the record keeper. A cluster, silent to the naked eye, but loud with memory. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.